Just posted on Twitter and Facebook. Live streaming is ready.
Okay.
Going live.
Can we get the closed captioning too, please?
It looks like Bob continued. He
Posted on
was
Twitter and
spared.
Facebook. Live streaming is ready.
I'm here.
Okay.
Going live.
Can we get the closed captioning too, please?
It looks like Bob continued. He
Posted on
was
Twitter and
spared.
Facebook. Live streaming is ready.
I'm here.
Okay.
Going live.
Can we get the closed captioning too, please?
It looks like Bob continued. He
Posted on
was
Twitter and
spared.
Facebook.
At the Howard
Live
Hewlett
streaming
Data
is
Science
ready.
I'm here.
Institute, we're addressing and solving
Can we
real-world
get the
problems
closed
through laying the
captioning too,
groundwork for the
please?
scientific foundations in the field of data science. We are developing new, innovative methods
It
and
looks like
infrastructure.
Bob continued.
Working
He
with
was
faculty
Posted on
at the
spared.
Howard
Live
Hewlett
streaming
Data
is
Science
ready.
and
I'm here.
industry partners. We're
To
addressing and
leverage
solving
interdisciplinary
real-world
Get the
knowledge
closed
through laying the
captioning
groundwork
too,
for the
please?
scientific foundation in the field of data science. We are developing new, innovative
April
methods
It
and
looks like
infrastructure.
Bob continued.
Working
He
Posted on
with
was
Twitter
faculty
and
at the
spared.
Howard
Facebook. Live
Hewlett
streaming
Data
is
Science
ready.
and
I'm here.
industry partners. We're
To
addressing and
leverage
solving
interdisciplinary
real-world
Get the
knowledge
closed
through laying the
captioning
groundwork
too,
for the
please?
scientific
What was only
foundation
supposed to be a
in the
month or
field of
two
data
has
science.
now turned into
We're
over a
developing
year
new,
working remotely
innovative
off campus
methods
It
and
looks
virtual
like
learning.
Bob continued. He
Posted
was
on
But
Twitter
that
and
doesn't
Facebook.
hinder
Live
our
streaming
success
is ready.
and
our
industry
impact
We're addressing
as
and
we
solving
celebrate
real-world
our
Get the
third
knowledge
anniversary
through laying the
at
groundwork
UC
for the
San Diego.
scientific
What was only
foundation
supposed to be a
in the
month or
field
two
of data
has
science.
now turned into over
We're
a year
developing new,
working remotely
innovative
off
methods
campus
and
with virtual
infrastructure.
learning.
Bob
Who
continued.
now
He
do
But
was
that
that
at the
doesn't
Howard
hinder
Hewlett
our
Data
success
Science and
Here.
our
industry
impact
We're addressing
as
and
we
solving
celebrate
real-world
our
Get the
third
closed
anniversary
laying the
captioning
at
groundwork
too,
for
UC
the
please?
San Diego. What was only
scientific
supposed to be
foundation
a
in the
month or
field of
two
data
has
science.
now turned into over a year working remotely off campus. 44% of our graduates are now working with various industry our impact
We're addressing
as
and
we
solving
celebrate
real-world
our third
knowledge
anniversary
through laying the groundwork
in addition to
Mhm.
Rajesh, are we all, everything going well? That was
Looks like that there was probably somebody who was having multiple windows open. So it was delayed playback. Might have been Bobby himself.
it was an example of the complexity of data because I kept on
Yeah. So I can't start the video, but see.
Sorry, on my part, I can't hear.
April 21st. It has been more than a month now since we have been in this great pause, working from home.
What was only supposed to be a month or two has now turned into over a year of working remotely off campus and virtual learning. But that didn't hinder our success, our impact, as we celebrate our third anniversary at UC San Diego. What was only supposed to be a month or two has now turned into over a year of working remotely off campus and virtual learning. But that didn't hinder our success, our impact, as we celebrate our third anniversary.
The video will have to wait. All right, let's start now. We have a little bit of a technical recursion difficulties with the videos, but we'll play back again. I want to invite our Executive Vice Chancellor Elizabeth Siemens to start the event.
Thanks very much, Rajesh. Good morning and welcome everybody to the third anniversary celebration of the Halajolu Data Science Institute, which was established on this date in 2018. It's a great pleasure to join you as we commemorate the vision and dedication of the university leaders and philanthropists who have made the Institute a reality. HDSI has already become a UC San Diego landmark that exemplifies the Triton spirit of collaboration and innovation. The faculty hires you are making in HDSI, the students you are admitting, and the innovative educational programs you are creating are simply outstanding. Data science has emerged nationally as a critical new field, one that both affects our daily lives and drives transformative discoveries. Notably, HDSI promotes the use of data science across far-flung disciplines and brings together students, faculty, researchers, and industry experts to tackle issues requiring input from multiple areas of expertise. Everything from ethics to statistics to entrepreneurship is in the mix. And so it is not surprising that in the academic aspirations our own university deans expressed most recently, hiring faculty jointly with HDSI was their most common ambition. Well, the progress that the Institute has made in just 3 years is really impressive. Not only has the undergraduate data science program immediately become one of our most popular majors, it's also one of the largest in the nation, and it continues to attract a diverse group of talented students and faculty scholars.
No, everyone struggles a little bit. It's normal.
New master's and doctoral programs are wending their way through the Senate review process, with further joint master's proposals already on the drawing board. And this rapid progression within HDSI exemplifies our current transformation as a university. Growth in numbers, in intellectual ambition, and in connectivity are all strengthening our ability to serve the people of California through granting more degrees, translating additional discoveries into action, and deepening community relationships. So all of us here are eager to see what exciting developments are on HDSI's horizon. Please use today's events as an opportunity to explore everything that data science has to offer, and in particular, to learn more about the people behind the Halajolu Data Science Institute. And now it's my pleasure to introduce one of those leaders, Senior Associate Vice Chancellor Robert Continetti.
Thank you, EVC Simmons. And it's truly a pleasure to welcome all of you today to the third anniversary celebration of the Halajolu Data Science Institute. I can't believe it's already the third anniversary. So I have the privilege as Senior Associate Vice Chancellor for Academic Affairs to serve as the Dean Designate for the Halajolu Data Science Institute, supporting Director Gupta in building this unique academic unit. I'm also a professor of chemistry, and while I generate and use a lot of data myself, I'm not a card-carrying data scientist. So I'll keep my remarks brief so we can move on to to hear about the true cutting edge in data science from the people in the Institute. Let me say this has truly been an interesting journey, and a number of important milestones have been achieved in the last year, marked by the first graduating class of the data science major, and also the recruitment of an outstanding cohort of both junior and senior faculty to join us. Of course, another chain of events that began almost exactly a year ago is our ongoing experience with the COVID-19 pandemic. I'm pleased to report that the faculty, staff, and students of HDSI have risen to the challenges associated with the precipitous switch to remote instruction and remote research. But of course, we really wish we could have had an in-person graduation ceremony last June. We missed that. And obviously we're meeting remotely today, but I'm confident that in the coming months, we'll increasingly return to in-person instruction and events. And I look forward to that, as I'm sure all of you do as well. As Dean Designate, I've observed that one of the most exciting things about the novel structure of the Halachulu Data Science Institute is that it is a true transdisciplinary academic organization, well positioned to develop and capitalize on the transdisciplinary field of data science. We see the impact of data science all around us, from how we interact with society, politics, economics, to the discovery of new patterns and processes in the universe, and the ethical foundations that are required to employ data science responsibly. At UC San Diego, I think we have the perfect place for making a data science institute like this successful. Interdisciplinary has been a strong tradition at our university since the very beginning. The foundation of our institution is a world-class transdisciplinary institute, the Scripps Institution of Oceanography. Now, with an outstanding general campus and health sciences campus also here in La Jolla, we have a scope of activity at UC San Diego that is second to none and provides an incredible environment for innovation. And HDSI is really proving that in spades. Innovating is what HDSI is doing, developing educational research programs that harness the power and prospects of data science for the future. With the leadership of Director Rajesh Gupta, the support of the faculty, and the academic leadership of the Executive Vice Chancellor and the Chancellor, we have made incredible progress over the last 3 years. An intellectual core has been established among the faculty, including those already at UC San Diego, as well as an outstanding group of new recruits. And we've built the infrastructure to support, as the EBC said, one of the largest undergraduate data science programs in the country. One really great thing about that undergraduate program is the capstone project. The first graduating class was last June, as I noted, but one of those capstone projects that the students engaged in, that we heard about at that graduation, and you're going to hear about an opportunity to hear more about today, are really, really incredible. I mean, you're really going to be impressed, I think, all of you in the audience. As the EBC noted, we are moving forward with a PhD and master's graduate programs. So those proposals are well on their way to getting the final approval of the Senate and the Office of the President. And that includes one of the first online master's degree programs at UCSD. So we're going to be an innovator in that area as well. Uh-oh, I seem to have frozen. Further innovation is being pursued, including a novel MD-MS program that's going to help provide the medical doctors of tomorrow with the data science knowledge that is becoming increasingly central to modern medical practice and research. Finally, as we continue to grow, we look for further opportunities to build on our strength in data science. We're engaged in discussions with the San Diego Supercomputer Center about synergisms with a goal to increase our research and educational effort in applied data science, leveraging the existence of that world-class high-performance and cloud computing center on our campus. So I believe as we mark this third anniversary that the future of the Halachulu Data Science Institute here at UC San Diego is bright. And it really has been one of the honors of my career to support the building of an effort like this that is going to have a lasting contribution to our society. So I would like to thank Tener Halachulu for his vision of supporting this, and I would like to thank Rajesh and all the staff and students and faculty of Halachulu Data Science Institute for making it happen. So with that, I would like to turn this back over to Rajesh so we can get on with hearing our distinguished plenary speaker, hear from some of the distinguished panels, as well as the faculty and students of HDSI as we go through today's program. Thank you. Rajesh.
Thank you, Bob. 3 years. I just can't believe I thought we took a pause for a month or something last year. Instead, it has been an amazing year. We have recruited people. In fact, they have been working with us for a year now, and we have not met them in person. We didn't lose pace. It was a year of many firsts. Last year at this time, when I came in front of you, we had just recruited 4 faculty members, 2 of which were on campus. Today, we have added 15 to that list, 4 of them jointly with other departments. We have graduated first class of our students in data science. We wrote up, discussed, and got approval for master's program, online master's program, and PhD program, all of which are right now moving through the system, wide approval. And while we are doing that, we already got started on our MD, MS program. So looking at 3 years, I think we are slightly ahead of our schedule. We had planned a trajectory in 5 years that we have now become a complete academic unit with graduate and undergraduate program and professional programs. With joint faculty, I was counting it last night, with 18 departments on campus, pretty much every single school or division on campus. So this has been a year HDSI came of maturity. But it also has been a year that has been very difficult for all of us. It was a year of not just working remotely with me, my jacket on and no shoes. But more importantly, it was a year of strife. It was a year of rancor in our public life. It was a year when we realized that the guarantee of life, liberty, and justice, or pursuit of happiness, is not equally given to all in our society. It was a year when we recognized whether the data is useful or not, but information definitely is very useful in misguiding and in disinformation, even in abusing information through multiple demonstrations. So here we are today at the opening of a discipline that we hope does more good to the society on balance, despite the evidence to the contrary in recent years, that becomes a force for good. It creates new talent, new awareness among all artists, all of us. So it has been a community that we put together to achieve just that goal, community of our faculty, staff, students, industry partners. It has been my distinct honor and privilege to be the strongest, the loudest cheerleader of this community, our friends and supporters. I know many of you have joined us. These remote meetings also make it possible for many to join, but also across different time zones. And I know some of our audience are overseas. Our advisory board, Eugene just landed in Dubai, so it must be late night. I'm very honored and pleased to see Ray Eller and Jeremy Ellman join. As you know, Jeff Ellman was my founding partner in building the Institute a year before we formally launched. Just a few moments ago, we received the approval to establish the first honored seminar series, Jeffrey L. Ellman Distinguished Lecturer Series in HDSI. from the campus leadership. And knowing Jeff as well as I do, I'm pretty sure he would have been very pleased with this recognition. Seminars and meetings were his particular thing. I'm also grateful to our Hallie Julie family, Anna Charlotte, Taner, and family Timur. They join us. And our advisory board of DJ Patel, Sanjay Jha, Arvind Jacobs, Eugene Iskabisky, Marty Cooper, Arlene Harris. Thank you so much. Most of all, I'm proud of our community we have put together. And it's a community, it's industry companies from biotech to technology to venture capital, but also civil organizations. SANDAG, Ray Major from the chief economist for San Diego Area Association of Governments, or Bahia Humphreys from Data Science Alliance, or Tech San Diego, San Diego Zoo. We have partners in every organizational elements of society. So this has been a fantastic journey for all of us, and thank you for joining us. We do have a good program put together, a strong program put together for you to look back and see what is coming up. I do want to say a few programming notes. Despite all the experience we all have in Zoom and other platforms, mishaps do happen. And if they do happen, we have our volunteers on the standby to fix any short-term challenges that might come. We are live streaming this into YouTube as well. We are using, or we will be using Slido event number 63637 as a means of question answer. In case of unlikely event of a Zoom attack or Zoom bomb or any of those, please do watch the website of the 3rd anniversary. There may be a momentary blackout if that happens. In the worst case, hopefully you will not notice it. Our countermeasures will take effect. We will communicate with you through our website and through our emails. Hopefully none of that happens and we enjoy the rest of the day. What I do want to say, we will take a few minutes to perhaps synchronize our next speaker as well. Maybe give another attempt at the video that our communications coordinator, Bobby Gordon, put together last night. So if all that goes well. And then I'll hand it over to our Associate Director, Dimitris Politis, for introducing our speaker, keynote speaker for this talk as well. So as we get online, Bobby, if you want to give it another try, and if you do have recursion problems, my apologies, we will synchronize later today on the video. Thank you so much for joining, and let's get the program rolling.
Can you hear me?
We can hear you, just not the video.
Oh, I see. Okay. But
And for me, the video is kind of skippy.
And prepare the future leaders of data science.
can you see the video now?
April 21st. It has been more than a month now since we have been in this great pause, working from home.
What was only supposed to be a month or two has now turned into over a year of working remotely off campus and virtual learning. But that didn't hinder our success, our impact, as we celebrate our 3rd anniversary at UC San Diego. We are proud to celebrate our inaugural graduating class of 75 students who now join the ranks of UC San Diego alumni. We awarded 29 undergraduate scholarships and learned from 27 senior capstone projects. Of our class of 2020, 44% of our graduates are now working within various industries, while 23% are pursuing further degrees and research opportunities. In addition, we welcomed 196 new data science students destined for the class of 2024. While leading our students through distance and remote learning opportunities, our faculty sponsored and participated in nearly 60 academic symposia and related events throughout the year. HDSI nearly doubled our faculty since our founding, forming a core group of 11 full-time faculty and 13 jointly appointed faculty, while also expanding our faculty council and faculty fellows. HDSI continued a strong industry partnership alliance program, now with 11 active partners and over 60 stakeholders. We welcomed 3 new partners, Epicor, Dexcom, and Thermo Fisher. And 26 data science students were mentored directly by industry leaders in our senior capstone projects. For example, our Deloitte mentorship program connected 14 leaders from Deloitte directly with 15 of our data science students, while our partnership with Intel across several projects involved 9 data science students, 6 HDSI faculty, and 11 mentors from Intel. We celebrated the launch of HDSI Career Services. In less than a year, Career Services hosted nearly 20 remote events, trainings, and programs, providing outreach, resources, networking opportunities, and support to our seniors, alumni, and industry partners. In a year off campus, HDSI also sponsored many large-scale programs throughout the year, including our Senior Capstone Showcase, Socially Distanced Triton 5K, Senior Orientation and Senior Open House, Data Science Talent Day, and many other events. We thank each of you who have been part of our success as we celebrate our 3rd anniversary. To our faculty, students, staff, alumni, industry partners, and UC San Diego collaborators, thank you for an amazing year.
Okay, I'm very glad that this worked. And it was actually a beautiful introduction. Thank you all. I'm here to introduce our keynote speaker. My name is Dimitris Kolitis. I'm Associate Director of HDSI. Well, Emmanuel Candes needs little introduction, but I'll say the obligatory few words because he has many awards to actually list. He's currently the Barnum Simons Chair in Mathematics and Statistics at Stanford, and also with affiliated position in electrical engineering. And he's also the co-director of the Stanford Data Science Institute, and we are very interested in what they're doing over there. So Emmanuel had a very illustrious career. He finished Stanford in 1998, if I recall, working with David Donahoe on wavelets and curvelets and so forth, and was already being noticed for this work. But then in Caltech, he moved and he was working for several years. He did some seminal work on nonlinear approximation and sparse estimation and so forth. And then what kind of happened is that Emmanuel, with Terence Tao and David Donoghue and their co-authors, essentially kicked off a whole new area of science, which is now called compressed sensing. And we have faculty in different universities focusing on compressed sensing. So Manuel is a member of the National Academy of Science. Like I said, he has received many awards. I will just mention the MacArthur Award in 2017. And we are extremely happy and delighted to have him as a keynote speaker and also member of our panel on research efforts in data science right after his talk. Before giving the floor to Emmanuel, let me just say I'll try to collect questions to Emmanuel on his talk based on the chat. So let's not interrupt Emmanuel if at all possible, because with 300 participants, this can easily become cumbersome. So, but if you put it on the chat, I'll kind of keep track on it, and we will have a 15-minute question and answer session at the end of the talk. So thank you so much, and let me give the floor to Emmanuel Candes.
Thank you very much, Dimitris. Can you hear me?
Yes.
Yes. So first of all, thanks a lot for the very kind introduction and the invitation to speak. I'm going to share my screen and hopefully you can see my slides. And just to make sure that you can see my slides, if that's not the case, you should just let me know, and so that I can proceed. But can you see my slides now?
Yes, slides are great.
All right. So as I said, you've been far too generous in your introduction. I wish I could be in San Diego right now and sharing this great day and this anniversary with all of you in person. Unfortunately, that's not possible. But I think, at least when we look at the state of California, I see great progress being done in terms of vaccination. And I hopefully will be able to visit your fantastic institute very, very shortly. So, having said this, thanks for tuning in. Today, we're going to talk about reliable predictions. In fact, we're going to talk about reliable counterfactual predictions a lot. And the goal of this lecture is to give you some idea of what's happening in a very exciting field, which I might broadly call predictive inference. So to get us started, I think we need to recognize that this is not work that have been done in isolation. I have several collaborators that I would like to acknowledge. First and foremost, Li Wale, who did the lion's share of the work I'll be presenting today, and a host of collaborators at Stanford and elsewhere that you see on the right. Now, the good news is that Li Wai is actually a participant. And so if you fire some questions on the chat, because Li Wai is actually on the call, he will be able to answer some of the questions you may have live. So to begin with, we need to talk about machine learning and we need to talk about critical applications. So as you know, machine learning is having more and more impact on our lives. And we begin to use machine learning in very critical applications. When I started to work at Caltech on some machine learning applications, the stakes were actually quite low. And it was mostly about predicting whether X or Y is going to like The Godfather or not, the famous Netflix problem. But now we use machine learning tools in more and more applications to make potentially critical decisions. For example, we use machine learning to drive cars, to make medical diagnostics, to decide who is going to get paroled or bailed, and so on and so forth. And so in many, many new applications, we're going to have to make simultaneous prediction from observations, which will trigger very important decisions. For example, who gets paroled, who gets bailed, what kind of treatment plan I'm going to give you after I've collected image data. And the question we want to ask in this lecture is whether we can have confidence in these predictions. So we live in a world where we need really reliable systems. It's college application these days, and the number of applications in pretty much every college in the US is exploding. And it's possible that at some point in time, we're going to automate a bit this decision process, and having software or machine learning algorithm that will try to quantify or predict how well a student will fare if admitted to a given college. And so, it's not impossible to imagine that we're going to have systems soon that will take lots of covariates or input, the high school you go to, your SAT scores, the courses you took, your extracurricular activities, and try to predict something quantitative about, let's say your GPA in college after 2 years. And so let's say that we have a system that does something like this and spits out a GPA of 3.62. This has tremendous consequences for whether to admit someone or not, and how we're going to make these decisions. Of course, there's enormous uncertainty about these predictions. And so the question I'd like to pose is why don't we see prediction intervals more often? So I think as the cost of the wrong decision becomes extremely high, we need to be able to tell quite accurately what we've learned from the experience of others, from other data points. And so what we're going to be advocating in this lecture is, it would be great is instead of returning point estimates, we could actually return interval estimates, intervals that have the properties that they contain the true label that you're trying to predict, let's say 90% of the time. And it's a bit different from what is actually the current practice of machine learning these days, where you basically tend to provide point estimates. But because the cost of the wrong decision can be high, it is important to be able to quantify what we've really learned from the experience of others. And there's no better way to do this than providing interval estimates. So we're going to talk about this, but we're going to talk about this. The reason why we don't see predictive intervals is, of course, that we use algorithms that are extremely sophisticated. And, here you see two examples of powerful machine learning algorithms. You see gradient boosting on the left, pioneered by Leo Breiman and my colleague Jerry Friedman, and of course neural nets and deep learning recognized by the Turing Award a couple years ago. These models are far beyond simple regression that statisticians were used to, and perhaps these models are so complex that this is why we cannot really quantify uncertainty. But we'll see, surprisingly, that this can be done. And not only this can be done, but this can be done very accurately without making any modeling assumption whatsoever. So we're going to talk a lot about reliable prediction in this lecture. And we're going to add a twist, which is we're also going to try to talk about counterfactual predictions. And counterfactual reasoning is, of course, everywhere. It's ubiquitous in modern science. And to give you a bunch of questions that we care about, or that a lot of people care about, we can just look at the field of causal inference, which is experiencing tremendous growth at the moment. And the typical question that people ask in causal inference is, what would have been a person's response, a subject response, had she taken the treatment instead of the placebo? Other instances of the same question can take several different forms. If we were to do policy evaluation, we might ask what would have been the outcome had the policy changed. It's not far from what we see in algorithmic fairness, where we ask typically what would have been the prediction had one belonged to another group, or even in explainable machine learning, which is what would have been the prediction or the output had the input changed. And so we want to answer questions of this kind. We're going to, of course, focus on perhaps the simplest case first, which is the simple case of causal inference, where we want to understand what the response would have been had you taken the treatment. And can we actually express this with the kind of reliable predictive inference that I was talking about before? So with this introduction, I suggest that we move into the topic of the lecture. And to describe what we're going to talk about, we're going to be in the framework of potential outcomes. So I understand that not many people, not everyone may be familiar with the framework of potential outcomes, which is was introduced by Neyman almost a century ago. And of course, a big proponent of this is Don Rubin. But it's very simple to explain. And all you need to really know about potential outcomes is a science table that I put on the right, where we have individuals, and we're going to call them units as is standard in the field. But we can think about them as being individuals. And each individual has vector features attached to them. These are the xi's, these are the covariates. And they may be assigned to either a treatment or a control group. And so these individuals are going to be treated individual, and the individual at the bottom will be untreated at individual. And so, of course, these individuals split into two categories, and there are two potential outcomes that I'm interested in. It's the outcome of an individual having received the treatment and an individual having received the placebo. And so if you're in the treatment group, of course, you only observed one of these two potential outcomes. You only observe the response to treatment, whereas if you're in the control group, you only observe the response to placebo. But really, their science table, as Don Rubin likes to call it, has really two columns where each individual has potentially two outcomes, one which is a response to treatment, and one is a response to the control group. And the problem is difficult because, of course, you cannot observe both simultaneously. You cannot receive both the vaccine and the placebo at the same time. You receive one of the two. And what we would like to ask is, what is the counterfactual? What would your response have been had you not received the treatment? Or if you are in the control group, what your response would have been had you received the treatment? And moving forward, we're going to make standard assumptions in the literature, which are listed on the left. It's something I'm happy to discuss perhaps after the lecture. There are standard assumptions in the framework of potential outcomes. And these are the assumptions that everybody makes in the field. Okay, so somehow, okay. So just to explain a bit what we're going to be talking about, let me just take the simplest possible case, which is that, you're performing a randomized trial perhaps, and you're going to assign treatment by tossing a coin, but which is actually based on your features, your covariates. So based on what people in the field we'll call a propensity score. And so individuals show up, we observe their covariates, and based on their covariates, we decide at random whether they're going to be treated or not. And the probability of being treated, given a value of the covariates, is what people call in the field called the propensity score. And of course, the probability of being untreated is the 1 minus the propensity score. And so individuals come in. Some of them are going to be red, and these are the treated individuals, and some of them are going to be blue, and these are the untreated individuals. And then we can bring about the science table of Don Rubin, where we also have the counterfactual, the things we would have liked to observe, but we did not observe. And these are this response in a bit shaded on my slide. And so we have the very light blue, which would have been the response for this individual who got treated had this person not been treated. And likewise, we have the potential outcome of this individual who received the placebo. And we would like to know what would have the response been if that individual had been treated. Okay, so we observe only one of the two, and we would like to infer the unseen response. Okay. All right, so just to make things a bit concrete, now we have this individual. She has received the placebo, but I would like to infer the value of Y1, which is a response that we would have observed had we given her the treatment. So, and to do this, of course, we're going to use the observed units. We're going to observe people who actually received the treatment to try to say something intelligent about the response that this person we would have observed if she had received the treatment. Okay, so now to go back to what I was saying before, the job that I'm proposing we set out to do is quite ambitious, because here's what we want. We want to actually construct a calibrated interval, which we're going to call in the rest of these lectures C hat of X. So it's a predictive range for Y1 of a control unit. That is, we want to actually construct a predictive range for each individual. We want to get a predictive range based on the value of their covariates with the following property, that if we could actually observe Y1, then it would fall in the predictive range 90% of the time. So let me just repeat this because this is important. What I want to do is I want to have a well-calibrated procedure that informs me about the potential outcomes that I did not get to see. So I take an individual. This individual had not been treated. She was in the control group. And what I'm asking is something ambitious. I ask, what would be the potential outcome for that individual who happened to be in the control group had she been treated? And so mathematically, what we want is we want to construct a set C hat that depends on the covariate X, so that the probability of the unseen outcome, given that you observe the other one, is above 90%. And so it's a form of predictive inference. What I'm trying to get at is to actually predict the unseen outcome. It's quite different from what most people are doing in the field, where usually the emphasis is on the conditional mean. I'm trying to predict the conditional mean, which is a conditional average treatment effect. Here, it's not what we care about. We don't want to predict the mean or infer the mean. We want to give a range for give a set of plausible values for the unseen outcome. And we're going to see how we can do this. Okay. So this problem is challenging for two reasons. Number one, we're not willing to make any assumptions on the distribution of the data whatsoever. And so the fact that I'm setting this goal might be seem to you a bit overly ambitious. And the second is that there's something at play here, which is important, and I hope this will come up in the panel, which is that we have a form of a covariate shift. You see, what I'm trying to do is I'm trying to infer the unseen response to treatment. So what you see over here, if you see the little hand that I'm moving around the slide, for an individual which has, for which the sampling distribution of this unobserved outcome is different from the data that I can collect. So I have the observed units, which are over here, the observed treated unit, and they have a distribution of covariates, and they have a distribution of the response to treatment given the covariates, and that distribution is not the same as the distribution of the control units. And so because the two populations differ in their distribution of covariates, and so there's a distribution mismatch between the data sets about which I can observe Y1 and the data set about which I want inference about Y1. And there is what machine learning and statistics is called a covariate shift. So just to give you a sense, there is, of course, the object of inference, which we care about, which is the distribution of the response to treatment given the covariate. But the two populations, the control population and the treated population, are different. And, for example, it might be, and this is, of course, a very simple example, it might be the case that I decide to assign treatment to individual because I see a low value of X. Whereas if you have a higher value of X, you're more likely to receive the placebo. So here I'm hitting on an important point, which is that we're going to seek inference about a population which is not the population about which we have data. Okay. So just to make sure that I drive this point home, we're going to use IID samples, the observed, treated, From a training distribution, this is what I'm going to call my training distribution. And this training distribution is in red. And these are the individuals who have been selected to retrieve treatment because they perhaps have the distribution of X has a certain characteristics. It's, the propensity score is what it is, times the probability of response given X. But the inference I'm looking for is under a different distribution, the target distribution, which has a different distribution of covariates because they received the placebo. And so what I want is I'm going to have a covariate shift. I'm going to have a distributional shift from training to testing. And yet I want exact inference for the test data. Okay. So now this covariate shift is, of course, well known to people who work in causal inference. There's going to be what I want to call the likelihood ratio between the target distribution and the training distribution. And this likelihood ratio is essentially the ratio of propensity scores. And so you see it very clearly on the slide. The likelihood ratio between the target distribution and the training distribution is a function of the propensity score. Okay. All right. So now we're going to try to solve this problem. Now that we pose the problem in terms that I hope are clear, we're going to try to solve this problem. And we're going to solve problems by applying 3 ideas. And first and foremost, I want to give a big shout to Vladimir Vogt and his colleagues, who started a wonderful field of research called conformal inference. And through 2 decades of work, what Vladimir Vogt and his colleagues have shown us is how we can actually achieve valid predictive inference. And let me just show you what they've managed to do. If you give me training data, which are distributed as, have a joint distribution Px times P of Y given X, what Vogt and his collaborators have done is that they have shown how you can construct valid predictive interval for unseen data. And so they are valid in the sense of what I advertised before, that based on the training data set, you can construct a function C hat, a predictive interval C hat, that will have the property that on future samples, the probability of coverage is 90% or any level you like. And this is a big development that is very exciting, and that has changed, when I got to learn about this, has changed the course of my research about 2 years ago. Now, this work is fantastic, but I had some doubts about the algorithm that they were using to actually achieve this goal. And so what you'll see next is a better algorithm to achieve the same goal, which we're going to call conformalized quantile regression. And from now on, I'm going to use CQR, which will be a method whereby we can construct predictive intervals with the advertised coverage. And so it really follows in the footstep of Vladimir Vogt and his colleagues, but I think it's a better algorithm. And finally, this does not address the issue of covariate shift, which is so central to counterfactual inference. And we're going to use a third idea, which I developed with Wayntip Shahani, Rina Barber, and Aditya Ramdas, to actually address the shift between training, right? The training distribution and the test distribution, which are different. And so now I suggest that we develop a solution and see how well it performs in practice. So just to set up the stage, of course, if I had an oracle, and if the oracle knew the distribution of the response Y1 given covariate X, so on the X-axis, you see my covariate X. On the Y-axis, you see Y. And if, of course, I knew the distribution of Y given X, then, of course, I could, for every value of X, I could calculate the upper and lower quantiles, and my problem would be solved. And you don't need statisticians to do this. But of course, we don't see the distribution of Y given X. In fact, we're not willing to make any assumption whatsoever about what this is. All I get to see is a cloud of points that might look something like this. And now what I want to do is I want to get carefully calibrated predictive intervals. So how are we going to do this? So the method is quite simple. So I'm going to present the conformalized quantile regression algorithm, or CQR for short. And it's basically going to do a very simple thing, which is it's going to bring together ideas from statistics and from quantile regression with Wolf's idea on conformal prediction. And so this is a very famous paper by Conker and Bassett. And so what you do is, we suggest you do is you run your favorite quantile regression algorithm. And so maybe you're a neural net person, or maybe you're an XGBoost person, or maybe you're a random forest person. And instead of using a squared loss, which is basically just trying to find the conditional mean, you're going to use what I think is cutely called a pinball loss, something that looks like this, where let's say alpha is either 0.05 or 0.95. And when you use alpha equals 0.05, you're going to get the 5th percentile, or an estimate of the 5th percentile of the distribution of y given x. And when alpha is 0.95, you get an estimate of the 95th percentile of the conditional distribution. So all what you do is you take your favorite machine learning algorithm and you just change the loss function so that instead of estimating the conditional mean, it estimates perhaps the conditional quantiles. Now, of course, you have to, that would not be a well-calibrated interval. So, and we're going to need to calibrate this. Of course, I'm sure a lot of you work in machine learning research and fit neural nets a lot. And you know that you can drive the error of a neural nets to 0 in any loss, with any loss function you care about, because you can perfectly interpolate the data, in which case your two quantiles would actually be the same. So how can it be a well-calibrated interval? So we need to calibrate what you would get from machine learning. And the way we're going to do this is I'm going to take your data set and split it into two halves. They don't have to be 50-50s, it can be 80-20. And on the first half, I'm going to perform what I just said, I'm going to perform quantile regression with your favorite machine learning algorithm. Let's say it's going to be neural nets. And so I get a lower quantile and an upper quantile, and now I'm going to calibrate it on the holdout data set. And how am I going to do this? So on the holdout data set, I'm going to, of course, draw my quantiles on the holdout data set. And for each green point, which is a calibration point, I'm going to compute a score. And this score is very, very simple to calculate. It's going to be quite simple. So we are on the left here, and we're going to score how well my predicted quantiles fit the calibration set. And so I take a point in the calibration set, and I compute its distance to the nearest quantile. And I'm going to assign a plus sign if the point is outside of the predicted range, and a negative sign if the point is inside the predictive range. So I'm just measuring the distance to the nearest quantile, and I'm signing the distance, and the distance is positive if I'm outside the predicted range, and the distance is negative if I'm inside the predicted range. And so mathematically, the definition is at the top. Okay, and then I'm going to calculate, let's say I have 300 calibration points. I have therefore 300 scores, and I can look at the density or the histogram of these scores, and that's what you see on the right. Okay. But now I remember that there is a covariate shift, which is that the training distribution does not look like the testing distribution. In particular, let's just maybe extreme. Let's say that the testing distribution has no point with x less than, let's say, this value, or that only you're in a testing set if and only if, let's say, x is bigger than a given cutoff, then of course the points on the left of this cutoff would be hardly relevant in making predictions. And so a bit more subtly, there is a covariate shift Wx. There is the covariate shift Wx, which is a likelihood ratio that we've seen before, which is in the case of a randomized trial would be proportional to the ratio of propensity scores, Wx. And what this is asking me is going to ask me to downsample some conformity scores and upsample other conformity scores. And the formula is over here. So what I'm going to do instead is I'm going to recompute an histogram of these conformity scores, but weighted by this likelihood ratio. And so now, instead of having, now instead of having this histogram, which I would get if I were not take into account the covariate shift, I'm going to get the histogram on the right, which takes into account the covariate shift. And now what do I do with this histogram? I'm going to compute the quantiles of this histogram, the 90th quantile of this histogram, which is what you see over here. So I compute my conformity scores, I reweight them to take into account the covariate shift. I compute the quantiles of this histogram, the 90th percentile of the histogram. So that's what I'm calculating. And now the procedure is very, very simple. It says, you want a predictive interval for future observations. That's easy. What you do is you just take your naive estimates and you adjust these naive estimates by the quantile of the weighted conformity scores that you just calculated. It's a very, very simple procedure. And the procedure is summarized on the next slide. And here it goes. You fit conditional quantiles of y1 given x. You use the observed treated units to do this. You fit your neural nets with the pinball laws that I mentioned. You compute non-conformity scores. You compute the quantile of the weighted conformity scores. And then you adjust the naive prediction, the uncalibrated prediction you were doing before with this quantile Q of x. And the remarkable result is this, which is that this just delivers exactly what we wanted, which is that for a person that was actually in the control group, the procedure, as you see above, achieves exact coverage. And it's not, as you'll see on simulation, it's not that it's about to achieve exact coverage, it achieves exact coverage. And so what you have is that the guarantee, you produce a range which is at least 90% and rarely above 90%. And I think what is exciting about this is that if you follow what I've been saying, is I've made no parametric or modeling assumption of any kind anywhere. So this works no matter the sample size, no matter the distribution of the data, and even perhaps surprisingly, no matter how you fit your conditional quantiles. Okay, so this is what the theory says, and for people who are expert, of course, this relies on knowing the weights, that is, knowing the likelihood ratio between the target and training distribution, and of course, in general, for observational studies, for randomized trials, you would know it, but in observational studies, you would not know it, so you would have to estimate the propensity scores. And we have a lot of theory with Liwa which shows that if you do a decent job at estimating the propensity score, the method will achieve validity. And this is a bit in the spirit of what you see in the literature in the form of double robustness of average treatment effects. But I'll skip this. So just to show you some examples of how that might work in practice, first, a simulation data set, which is taken from Stefan Wager and Susan Athey. It's a very simple data set. It's a simulated data set where, you know, the response to treatment is modeled as a Gaussian with a variance that is changing depending on the value of the covariate. The propensity score is also changing smoothly as a function of the covariates. But otherwise, the problem is fairly simple. And so then, of course, we ask about counterfactual inference. But of course, we don't know what the model generated the data, because nowhere in the method I proposed, you need to know about it. Here, you're going to see results done using the conformal causal package of Liwa. And this is a little plug, something that you can reproduce the experiments you're about to see. And so when we look at this method, and by the way, this method can wrap around any Bayes learner to learn the quantiles. And so we used a lot of things. We used BART, which is Bayesian additive regression trees. We use gradient boosting. We use RF. And when you see CQR in front of it, it's been conformalized. It's been calibrated using the algorithms that you've seen. And this picture is quite boring, because if you look at the coverage of the method that we've discussed, those that start with CQR, you know, you want 90%, you get exactly 90%. No matter the dimensionality of the problem, no matter where the noise is heteroscedastic or not, the plots are very boring, because the box plots sharply focus around 90%, and that's the theorem I was giving you. Now, of course, if you use methods from the causal inference literature, they would, of course, not cover the missing outcome at all. In fact, the coverage would be quite low, but that's, of course, to be expected, because these methods are actually targeting the mean and not the response itself. But as you'll see, it is our experience that they don't really do a good job at covering the mean either. But what we can see from these plots is that no matter what setting you're in, you achieve 90.05 or 19.1% coverage. This is a view of length. And so here we see that, you know, if we look at, for example, this plot, the blue line is, well, if you knew the grand truth, you know, if you knew the grand truth, if you knew the distribution of y1 given x, then of course you could calculate the quantiles exactly, and you would be able to actually draw intervals with these average lengths. Here, I think what's interesting about this plot is that we can see that, for example, when I wrap the CQR around Bayesian additive regression trees, we see that the width, that the length of the intervals that are produced by this method is not much greater than the optimal lengths, which would be only achievable if I knew actually the data generation mechanism. And so this is showing that BART, at least in this example, is quite powerful at estimating quantiles. They're then calibrated to achieve perfect coverage, and the length is almost right. Okay, this is plots that are important, which show coverage across percentiles. You know, I've told you that the variance of the response depends on X. And so here what I show you is I show you the conditional coverage. That is the coverage, the achieved coverage of this method. So just look at CQR. The coverage of this method as a function of the amount of variance there is on a percentile scale. And what we see here is that we see that no matter the underlying value of the conditional variance, the coverage is really around 90%, which is of course not true for the method that have not been calibrated. Okay, so something that I personally find a bit disturbing is that with Liwa, we looked at a lot of methods that are popular in causal inference, X-learner, causal forest, and we look at whether there were covers or the parameter of inference for this method, which would be the mean shift between treatment and control. And in all our experiments, they failed and sometimes spectacularly failed at getting anywhere near coverage. While of course, our method would achieve coverage and more because they cover more than the mean. They actually cover the response. So we can go a step further, and one step further in causal inference is to actually say something intelligent about individual treatment effect. And what we have here is, they are individuals. These are the data I have. They've been untreated. These people have been treated. And now I'm going to take a random individual from the population. And I'm asking, how can you say something? Can you actually predict a range for what people call the individual treatment effect, which is for an unseen individual, what is your prediction about y1 minus y0? And with Liwa, we have shown that you could actually adapt the method you've just seen to actually achieve this. So you can actually give ranges of observation that are plausible values for individual treatment effect, achieving 90%, exactly 90% coverage. Okay, but I see that I'm a bit out, my time is up, so I have a lot of simulations to show you, but in the next 5 minutes, I would prefer to broaden the discussion a bit because I know that perhaps at your institute, not everyone is interested in counterfactuals. And so rather than discussing the accuracy with which we can estimate individual effects, treatment effects, let me just try to lighten up the discussion a bit and go through potential other uses of the method you've just seen. There are two things I would like to talk about. First is the election night at the Washington Post, where you'll see, which is very connected to what you've just seen. And the second is a little personal take on algorithmic fairness, which is a term I hate, and I prefer the word equitable treatment. So just to see where these ideas can take you, let's look at the Washington Post first. By the way, I need to say that this is not my work anymore. This is the work of a wonderful student, John Chirian and Lenny Bronner, who works at the Washington Post desk. You know what this is. This is how each county voted in 2016 in the presidential election. We have about 4,200 counties, and you see a county, a map, a detailed map of the United States showing you how each county voted. And San Diego, you can see San Diego at the bottom of California. Okay, and so what the Washington Post was trying to do during election night is to try to get an accurate forecast of how each individual state would turn out when every county had reported. And so what they have for each county is they have data XI, YI. XIs are county features, and they are the type that you might expect, quantifying perhaps various features about a county. Is it rural? Is it not? Is it urban? Is it suburban? What's the median income in the county? Various types of demographics and so on. So these are the features. And YY is, of course, the response we care about. And YY can be, for the Washington Post, was several things, but one of them was, for example, the number of Democratic votes for Joe Biden. And of course, it was renormalized in this case to be the number of votes for Biden for the Republican or the Democratic candidate in 2020 minus the number of votes in 2016 over, so the percentage change in the number of votes for the Republican or the Democratic candidate. And what the Washington Post wanted to do, they wanted to give their readers an accurate view of where the election might end up, taking uncertainty quantification into account. And so what they wanted to do is they wanted to use reported counties to forecast unreported counties. Exactly the problem we talked about, where you have a training set, which is what you've seen in reported counties, and now you try to infer the response that you have not seen which is the unreported counties. And of course, as you can imagine, through that election night, it's not that I pull counties that have an urn so that the training distribution is the same as the testing distribution, because you know very well that for perhaps rural counties tend to report early, urban counties report late, and so you have a covariate shifts in the way counties reporting. And so the data experience undergoes a covariate shift that you need to correct, which said that roughly what you have not seen is not exactly distributed as what you've seen. And so you're going to need to reweight the data to match the distribution of covariates in unseen counties. And so what John and Lenny have done is actually adapted the conformalized quantile regression algorithm to predict with error bars to give predictive intervals for counties that have not yet reported based on what we've seen so far. Now, of course, you know, you need to be careful about how you do the covariate adjustment. And here they had an advantage, which is that they could look back and they could actually test the adjustment they were doing based on which in finance you might want to call back testing, going from the 2012 election to 2016, so that they could see that they were actually doing something sensible. And if they were not, then it meant that they had to reweight counties a bit differently. But at some point, they convinced themselves that their reweighting scheme in backtest was performing well enough that they felt confident that they could go live. And indeed, they went live. And so when you looked at the Washington Post, throughout the election, from the night of the election up till 7 days later, of course, a lot of eyes were focused on Pennsylvania. And you had this weighted conformalized quantile regression algorithm running in the background, making predictions, calibrated prediction on how Pennsylvania would turn up. And here you see a snapshot of on November 5 at 12:50 a.m. And I think their graphics were quite amazing. And at the same time, on November 5, 2020, you could actually predict that Joe Biden had a lead, even though he was down in the number of votes, but that he would actually end up on top. And they had some very cool graphics to actually show you the degrees of certainty with which they were confident. And this was just a conformalized quantile regression algorithm running to actually give these measures of uncertainty. Okay, Dimitris, maybe I'm out of time. It's time to wrap up, or can I say a few words about fairness?
Yeah, a couple of minutes on fairness, sure.
If I have 2 minutes, just maybe just one thing, and okay, we'll see. So maybe I won't go through my spiel about algorithmic fairness. You know the consequences of using machine learning in critical applications, you know, and the bad things that are associated with it. So what I want to say is this is a school of data science, and you know what is our responsibilities about data science is to communicate uncertainty to decision makers. When we use fancy algorithm, we should not overstate what we've inferred from a neural net or XGBoost or whatever. And of course, we need to do no harm. We need to treat people equitably. And so there's a lot of machine learning literature at the moment focused on fairness. I'm a bit, to be honest with you, I'm a bit uncomfortable with this literature because a lot of this work is about baking in the algorithm some notion of fairness. And I've been talking to legal scholars about fairness and other people, and it's not exactly clear what fairness is. You know, fairness means different things to different people. And in fact, if you look at US courts, there is no agreement on what fairness is. As a result, I think it's extremely important to decouple the risk assessment problem, the statistical problem, from the policy problem. And that's not what you see in the current machine learning literature, where actually a notion of fairness is encoded into an algorithm. And I find it problematic because people don't even agree on what fairness means. So how can you encode it in an algorithm? So I prefer this view of the world where they are decoupled, and I need to solve the risk assessment problem. And then there's a policy problem, which is decoupled. It's not because the fact that I can predict correctly that a certain defendant has a 20% chance of committing recidivism does not dictate a policy in and on itself. So there are two things that are separated. So how do we communicate to decision makers? Well, you've seen ideas, right? So, you know, what I've learned. So if the goal of what we do is to learn from data, what is it that I have really learned? And so the technology that you've seen in this lecture would allow you to do something like this, which is, well, so for example, I can say, you know, I have some data, and what I can do is you're interested in outcome Y, I can give you a predictive range, C of X, which has the property that this predicted range is actually covering the true label. It reflects, it's an honest accuracy, an honest quantification of my uncertainty. The label is within range exactly 90% of the time, and it's unbiased in the sense that we can actually tune this calibration so that this statement is true no matter whether you're white or non-white, whether you're male or female, and so on and so forth. So I really like this way of thinking about equitable treatment, where I'm going to learn from data, and the way I'm going to communicate to decision makers is to say, here's a predictive interval, and it does not matter which group you belong to, this interval is correct. And if the interval is long, so be it. This is what you've learned, and you're fooling yourself if you think that you've learned more than this. So, you know, we've actually played with this, and we actually looked at this on some data sets. And so here's a data set about healthcare utilization services. And we have lots of features, 140 of them, you know, marital status, age, poverty, functional limitations, the kind of insurance you have, and so on. And the goal is to predict healthcare utilization, perhaps measured by the number of visits to a doctor or office, hospital, and so on. Just to give you a sense of what happens when you fit machine learning algorithms, sophisticated algorithms, data of this kind, what we found empirically is that, at least in this example, it might not be true in other examples, but a neural net would typically overestimate the response of the non-white group and underestimate the response of the white group. So if anything, it seems to be a bit biased against non-white. What you can do with the method you've done is you can adjust it. You can say, you know, first of all, I should not give you a point estimate. I should give you a range. And you can calibrate it so that the range is actually correct no matter what group you belong to. And so that's what CQR will do when properly calibrated, depending on the group you belong to. Okay, so I talked a lot, but I think the goal was to show, basically try to understand when we have data and we fit fancy machine algorithms, things that we have a difficult to understand mathematically, like neural nets or XGBoost, what have we really learned from the experience of others? I basically discuss adding protective layers around these machine algorithms that you have results that you can trust. I think your institute is fantastic. There are many other topics I would like to discuss, especially when it comes to algorithmic fairness. It's important that we give the fact to decision makers. We're not decision makers ourselves. We need to provide the fact to decision makers and not bake in ideology into algorithms. And with this, I want to thank you very much for your attention.
Thank you very much. I will not ask people to clap because that caused a bit of concern. Thank you very much, Manu, for this stimulating talk. So this subject matter of predictive inference is actually very close to my heart. But I will take my turn, and I will first ask a question that was posed, and it's actually pandemic related. So do you think that CQR is better on recommender system better than Netflix?
See, so by the way, we're not a substitute for machine learning algorithm. What we're doing is we're calibrating. So CQR is not an algorithm. It is really a protective layer around a predictive algorithm so that now what comes out of your machine learning algorithm is well calibrated. So perhaps let me try to understand, to answer this question by going back into the presentation a bit. And let me see if I can go back. So when we looked at the accuracy, so the question is, in the end, do you have bands that are narrow? And, there's a trade-off, there's a fundamental trade-off of statistics, which is, I want coverage, but I want coverage with an interval which is as informative as possible, that is as narrow as possible. And this is where the quality of the training algorithm you use will be crucial. So if you use a sloppy machine learning algorithm to learn the quantiles, then in the end, you will get calibrated interval, but they will be very wide. So for example, suppose you make no effort in actually learning about the quantiles during training. Then, suppose you make no effort, so you say Q hat is 0. Then what the method will do typically is it will return essentially the marginal quantiles of Y. And they might not be very good. They might be very wide because, X has explanatory power. So it's a very important question, but let me just emphasize that I'm just building around machine learning. I'm wrapping around machine learning. And this method will be as good as the machine learning algorithm is, but then they will be well calibrated. Did I answer the question, Dimitris, you think?
Yes, I do think, and let me actually give the chance to a couple of other people to ask a question. So David Danks had a question on public policy. I don't know, David, do you want to ask it directly? Maybe you can phrase it better than me.
Sure, I'm happy to. Thanks for a really wonderful talk. My question was about the effort to separate statistical and policy challenges, which I think is, in many cases can be done, but I worry that in cases like, say, the recidivism case that you discussed, there are policy relevant aspects that are baked into the training data in the form of, say, police practices for rearrests. Yes. And so I guess I wanted to push back a little bit about whether there really is the clean separation that you want to have in many real world social cases.
Yes. So this is a very, very good point, which is that, and I think when statisticians get to work, the first thing they ask is about where does the data come from? Is the data biased? Is it not biased? And so there's a form of data quality control that need to be exerted. And so I did not mean to imply that you could just do this. The bias in the data you get is extremely important and is completely orthogonal to what I'm suggesting here. So I'm very happy that you asked this. It's possible. It is often the case that you need to apply that data quality control before you can do any kind of statistical work. And I did not talk about it, but it needs to be done. And so this is not a solution to this. So thanks a lot for bringing another important distinction. This will not eliminate biases that you have in the data.
Okay, great. Thank you. So we have time for one last question, but I have to ask both person who will ask the question and Emmanuel to just limit to 3 or 4 minutes. So let me give the floor to Armin Schwarzman because they had a big exchange with Lihua Lei.
Oh, I see. And can Liwa answer this question? Because Liwa has an IQ which is about the square of mine. So if the question is too complicated,
Okay, Armin, would you like to ask a question?
Yeah, so I will ask you the question that Lihua did not answer. Hi, Manuel. Thank you. This is super interesting. I've been listening attentively. So my experience in teaching and trying to teach prediction intervals, even in simple situations like regression, is one of interpretation. Mm-hmm. So even teaching confidence intervals is already difficult. But usually what you say to people is that the probability is 90% probability that we're discussing, we're talking about for confidence intervals, is over repeated experiments. So if you were to repeat the experiment and recollect the data, let's say 100 times, then in 90 of them, your interval would include the parameter of interest. For prediction, it's harder because it's not entirely clear if we're talking about repeated experiments where you recollect the data, or if it's just the probability that concerns the distribution of the new point that you would be observing for which you would be trying to predict. So I'm trying to understand what is the interpretation of the probability that you're using for these prediction intervals.
So these prediction intervals, the coverage holds in a marginal sense. And I have to be very clear on what that means.
Right.
It means that but it's what people do in machine learning also, right? So when we say, when we make a claim about root mean squared error, it's not conditioned on the training set. But let me just explain as best as I can, what the average is taken over. First of all, it's a prediction over a future point. So there's a person I have not seen, and that person has an X and a Y. And so I want to know whether Y is included in the prediction set C hat that I constructed from the training data. And I say, the theorem says, so when I say this, okay, so maybe I'm going to move here to the next slide if I can. When I write down my statement, it's an average over two things. One, a future observation, and two, the training set. Now, with Liwa and Stephen Bates and Yaniv Romano, we are moving away a bit away from averaging over the training set. But the way I've stated them, it's an average over a future test point and the training data I gave you.
Thank you.
But what you can ask is you can ask a form of a different question, which is, can you actually condition on the training set? And that's what we're working on at the moment. And it's very important, your question, because if I create a system that I want to deploy, the system has been fit on the training set, and now it's not going to move. So it's important to condition on the training set. In other applications, it's more about comparison of algorithms, then it's the method the criterion we have is more applicable.
Great, thank you.
Okay, thank you so much. Thank you, Emmanuel, for the amazing talk. And we are moving now to the next part of the program, which is the panel on research ideas and on data science. So Emmanuel will join us, and Jelena Bradic is the moderator. So Jelena, the floor is yours.
Okay, welcome everybody. It's a great pleasure to be a moderator for our morning panel on research challenges in data science. I'm Jelena Bradic. I'm an associate professor of statistics, and I have a joint appointment in math and HDSI. Let me first mention that we will collect all the questions till the end on Silo. And so let's not interrupt the panel. And I would like to begin with a brief introduction of our four acclaimed panelists. So I'll go in alphabetical order. The first is Emmanuel Candes, who just gave a wonderful talk. He's a Barnum-Simons Chair in Mathematics and Statistics at Stanford, and also a co-chair of the Data Science Institute at Stanford. Thank you, Emmanuel, for joining us. Emmanuel has won numerous awards, for his research, one of which is the MacArthur Genius Award. Then we have Jennifer Shays, if I'm saying it right, who is an associate provost of the Division of Computing, Data Science, and Society, something brand new at UC Berkeley, and also the Dean of the School of Information. Thank you for joining us. She's also a professor at the Electrical Engineering Department, Mathematics and Statistics, and School of Information. In her previous life, she founded and led interdisciplinary labs at Microsoft Research, both New England, as well as New York, as well as Montreal. So yeah, thank you. Then we have Terence Sejnowski, who holds a Francis Crick Chair at the Salk Institute for Biological Studies. Thank you. You go by Terry. Can I call you Terry? You're muted, sorry.
Yes.
Thank you. So Terry is a distinguished professor at the University of California, San Diego, and has been a member of the advisory committee of the Obama administration for the BRAIN Initiative, and was the president of the Neural IPS Foundation, a very famous ML venue. And lastly, we have Jeanette Wink, if I'm saying it correct, who is an Evanescence Director of Data Science Institute at Columbia University. Thank you, Jeanette, for joining us this morning. In her previous life, she has been at various locations, Carnegie Mellon, a distinguished professor, as well as Microsoft Research. She's also a professor of computer science at Columbia University and has been well known for her work in privacy and security. So thank you for joining me and all of us today. So the format of the panel will be kind of directed through questions, and I will ask each panelist to chime in, but I will probably direct one question at each panelist initially, okay? So let's begin with, it's a good introduction since our panel is called Research Challenges in Data Science. So Professor Wing, you have written a recent discussion article at the Harvard Data Science Review on the 10 research challenge areas, and you made a point that those two are not the same, in data science. As you notice, although data science bases and builds knowledge from multiple disciplines, computer science, statistics, mathematics, data science is a unique field with many mysteries, right, to unlock and develop. And for example, among other areas, you mentioned causal inference, robustness, stability, computability, and others. So could we begin by discussing, could you give us your thoughts initially, or could you highlight a few research areas of data science that you particularly cherish or you want to share with us? So please go ahead.
Thank you. I am hardly going to use my 2 minutes of time here to talk about 10 research challenge areas, but the ones that you mentioned are near and dear to my heart. If you read the 10 research challenge areas, I try to order them in sort of the more scientific, technical, theoretical, like understanding why deep learning even works, to the more societal, the last one being specifically on ethics. You mentioned causal reasoning is a pet favorite of mine right now, because I think that so much has been done in terms of correlation, association with big data and machine learning, but there's also great interest in inferring causality. And it was actually my time at Microsoft where I really came to understand the importance of causal reasoning, but also the meld, and I really want to credit Jennifer for this, of bringing in the sensibilities of economists and political scientists and so on, whose bread and butter is to infer causality, and then the meeting of the minds by bringing together the machine learning people and the economists. I really was educated in the potential. And I think it's just potential right now. There's a lot more we can do. But I do want to speak about one favorite area of mine, and this should not surprise many of you. It's an area that I call trustworthy AI. And there's it's a little paragraph in my article, and I'm happy to say that just recently CACM accepted an article on trustworthy AI that will come out where I elaborate more on that one paragraph. And I want to make 2 points about trustworthy AI. First of all, I come from a trustworthy computing background. For over 2 decades, the academic, corporate, and government communities have really been promoting security, privacy, reliability, availability, usability, and all these properties of trustworthy computing. And again, a nod to Microsoft for putting its neck out early in the 2001 Bill Gates memo on trustworthy computing to take a stand on that. But NSF took a stand as well. And so when I talk about trustworthy AI, the first thing I want to emphasize is that it's not just those properties that we know of with respect to trustworthy computing, like security and reliability and privacy and so on. It's additional properties that we're now in our face with respect to AI systems and how they're being deployed in practice. And I'm talking about properties like robustness and fairness, interpretability, and properties that we don't even know how to formalize. So I think trustworthy AI as a term ups the ante in the kinds of properties we care about for making a system trustworthy. The second point I wanted to make is, again, for those of you who know my research history in formal methods and specification and verification, in my upcoming CACM article, I talk about one approach towards achieving trustworthy AI. And this is, of course, in using formal methods. However, the existing formal methods fall far short of what we are able to do in terms of specifying, let alone verifying an AI system. And this is because of the inherent probabilistic and stochastic nature of AI systems. And as a computer scientist, we're trained to think in terms of discrete logic, true or false, on or off, 1 or 0, yes or no. And AI systems, first of all, they have to deal with a lot of uncertainty in the environment. So it's not yes or no, it's some probability. And then they're inherently probabilistic animals in terms of what are on the edges in a DNN. And there are other aspects of AI systems or machine learning models more specifically that really up the ante in terms of what formal methods can achieve. The last thing I'll say, because this is a data science symposium, is what is, and this is a question I ask the community, the role of data in terms of achieving trustworthiness and especially in terms of a verification framework. We never have to deal with properties of the data before. We always were very keen to say, assert a property like for all x, p of x. Well, I think in the world of AI systems, we're hardly going to be able to assert any kind of for all x, p of x. So I'll stop then and let others answer your other questions.
Oh, wonderful. Thank you. And indeed, perhaps the limit of data or the role of data in data science is what defines data science, maybe. But I wanted to open the panel more broadly. So perhaps Emmanuel, we mentioned causal inference, we mentioned stability and the impact of data. So what are your thoughts on challenges in data science?
So first of all, thanks for having me in this panel, and hi Jennifer and Janet and Terry. I'm 100% with Janet, I have to say. You know, I was preparing. So first we got a cheat sheet from Yelena, and she asked us, you know, and I was thinking about what she should say. And to me, the thing that came to my mind was robustness. And let me just, two things, robustness and counterfactual inference. So counterfactual was the theme of the lecture. I'm not going to talk about it again because we talked about reliable prediction. We talked about counterfactuals for an hour. So no need to repeat myself. Let me give you an example. I think, you know, if I put an example in people's brain, maybe they'll think about it. But I'm totally with Janet on this. My colleague Brad Efron did an interesting experiment. He took prostate cancer data. And so you had patients and, you know, 51 had prostate cancers and 51 were controlled, did not have prostate cancer. And for each of these patients, I could see the expression levels of 6,000 genes. And what he did, he actually created a training set, he created a test set, and he fit random forests on his computer. And random forest achieved an incredible performance. Of the 51 test cases, he could predict 50. There's only one that was incorrectly classified. But then, and that's the point of what I want to say next, he created, these individuals had a sort of an extra covariates, perhaps indicating the time at which they entered the study. And then he created a test set, which was a bit for individuals who tend to enter the study a bit late, and a training set a bit early. And now the predictive performance of random forest completely collapsed. So what have we learned really? Did we learn when you enter the study? What did we learn? What did we learn from gene expression to prostate cancer? And so I think this example is extremely important nowadays, because still by and large, the practice of machine learning is to kind of randomize your training set and your test set. But as we talked during the lectures, the test set, that when you're going to apply your algorithm in the future, may not be the same distribution. It may have changed. And so how are you going to deal with this? And just to think about this, that on a very well-controlled data set, just by tweaking a bit how you select the training set from the test, and then all of a sudden your predictive performance collapses, it should give us pause. And what I want to ask is, what have we learned? And that's a central subject of statistics. So from here and now, what can infer in the future? And I hope, and I'm going to paraphrase Brad, which is, I'm hoping that we're not going to learn things that are ephemeral, that just vanish into thin air a few minutes from now. We see papers published in PNAS saying that, I don't know, if you like curly fries, you're more likely to have a high IQ. Well, it might be true in this data set, but is it going to be true tomorrow? Is it going to be true in a slightly different town? And I think that's, to me, the major challenge is, the world is dynamic. The future samples are not reproduced from the training set I gave you. And so when I make claims today, what can I say about tomorrow really? And I've used this as a central challenge of data science and its robustness. And I can talk forever about this, but I don't want to take too much of your time. So I'm completely with Janet on this one.
Well, thank you. Indeed, robustness or stability, or perhaps we need new definitions of what do we want? What do we mean by this? I think predictions outside of the data set is important, but perhaps we are lacking proper formal structure. So Jennifer, do you want to chime in, please?
Yes, and I have to say, I'm just going to pile on with Jeanette and Emmanuel. I think that robustness and causal inference are incredibly important. And of course, in the example we just heard, you should not have been doing causal inference given the fact that the distribution had changed. So what do we do in those cases? And I think one of the most exciting things for us right now is that the application areas which are reflecting urgent problems in society are really challenging the core of data science. They are challenging us to come up with so much more than we currently have. I'll just give a couple of examples of broad areas that we're looking at in my new division of computing, data science, and society. One is the area of social justice. And here, a lot of things are being algorithmically determined more and more. And of course, this is based on data, which might be getting used outside of its region of validity. So we have an example which is being worked on by a professor in computer science and a professor in law. I'm not sure whether you know this. When I learned this, it shocked me. But the output of algorithms is being used as evidence in capital cases. It is putting the output of algorithms is being used as the evidence to put people on death row. These algorithms are proprietary. So in general, we are not allowed to query them. The defenders are not allowed to query these algorithms. So they have started working with computer scientists and statisticians to try to understand what's going on. One of the most widely used pieces of software to put people on death row is being routinely used outside of its domain of validity. And so they are establishing that. And this is exactly, you know, the test set for it, you know, is not the actual set on which they're using it, and has significant statistical deviation from that. They're trying to send up a case to the Supreme Court now to get somebody off death row. So this is an incredibly important area that has the kinds of consequences that are just staggering. A second broad area is climate and sustainability. And here I think causal inference is incredibly important. We see a lot of correlation, and in fact, you know, all sides of the political spectrum, you know, use correlation to support their views on climate change. And so how do we really begin to do proper causal inference? Because the interventions that we have to make for everyone from, you know, someone trying to determine a policy at the local level about water, or, you know, to all the way up to the national levels, is we don't have proper causal inference. And how do we do that? And another thing for climate change, which I think is so important, is how do we try to do causal inference when the data is itself incredibly heterogeneous? And I'm not just talking about, you know, heterogeneity within a data set in one area, but some of these complex societal problems have really incredibly heterogeneous data. How do we deal with that? Even within a domain which sounds very well determined, like biomedicine, which is the example that Emmanuel just used. The data is incredibly heterogeneous. It's genomic data, it's immunomic data, it's clinical data. And so how do we learn to do proper causal inference on this incredibly heterogeneous data? These are all questions of, these are all fundamental questions for the field. They pose scientific challenges, statistical challenges. And yet we're seeing data being used much, you know, more and more widely. And how do we take on these challenges? How do we warn people when the data might be getting used outside of its domain of validity? And how do we come up with the breakthroughs in the statistical methods to really deal with this?
Thank you, Jennifer. Indeed, if I may add, it's the types of data that has also changed. It's not that the causal inference as a field has lacked somehow, but it's really the structure of the data, right? Observational versus interventional, homogeneous versus heterogeneous. And it ties up to the generalization issue and verification that we talked about. It's all like a big picture thing. So Terry, can we hear back from you, your opinions on challenges in data science?
Well, specifically on causal inference, I'm very, very careful about medicine. Medicine is an area where there's pitfalls. And Emmanuel was briefly mentioned observational data. And I just want to give one example of a pitfall. So there was an article that was published in New England Journal of Medicine, which is a very prestigious journal in medicine, in which they looked at the, you know, how much chocolate is consumed by populations in different countries and how many Nobel Prize winners they had. And lo and behold, you know, it's significant at the 0.01 level. I mean, this is really a very, very dramatic finding. It was published in this journal. So I teamed up with Beatrice Golam, who's a professor in the Department of Medicine here, because between us, we know about half of the Nobel Prize winners, living Nobel Prize winners in physiology or medicine, physics, chemistry. And we sent them a questionnaire and, do you like chocolate? Did you eat chocolate when you were doing your best work, for your Nobel Prize? And lo and behold, the data came back, and in fact, it was barely significant at the 0.05 level. And one of them said that, I don't particularly like chocolate, but my wife eats, she loves it. And I'm hoping she'll get the Nobel Prize. But it's, the problem is we didn't have a proper control. The proper control would be competitors, that your competitors eat chocolate more or less than you did. And of course, and the problem is with observational studies is that there's always confounders that you don't even know about. And there's many, many stories about how big decisions like, the hormone replacement therapy used to be extremely, they did studies and almost all women are on it. But the reality is that women in the study were all people who high economic status. And the fact is that if you look at the whole population, it's really not, it has a lot of side effects like cancer. So I think there's a lot of really important issues here if you start applying it to medical decisions, that these are known problems. I'm not sure if Emmanuel has thought through this, and maybe he has solutions to. He's very, very clever, by the way. I was really impressed by your talk.
Thanks a lot. So yeah, I know this paper actually. I used it in many lectures. Thanks, Terry, for bringing it up. I'm amazed by this discussion, to be honest. And I think because I think you asked for careful statistical thinking and reasoning, and I did not expect the conversation would be so much about how we need to be careful about statistical reasoning. And maybe I want to pivot in a different direction. So here's one, a challenge. So Yelena asked us about challenge. Let me go and talk a little bit about education. And maybe this is my experience, and then I'll let the other panelists comment on this. But I find that we have managed to democratize the computational tools. That is, it's easy to go in a classroom and ask students to fire up TensorFlow and use scikit-learn and use PyTorch and all that. But I don't know that we have democratized statistical reasoning. And when I hear you talk, it's all about the importance of statistical reasoning. And we know how to teach how to use tools. And do we know how to teach statistical reasoning? And I'm very curious to hear your thoughts about this.
That's excellent. And Jennifer, please go ahead.
So, the data science major started at Berkeley little less than 3 years ago. The class that will be graduating this year has 700 majors. It is just, what I love about it is that we have a lot of EECS majors and letters and sciences CS majors. The data science major has 4 components. It has statistics and some probability. It has computing. It has human context and ethics, which I actually think is really important, and a disciplinary emphasis. And in that disciplinary emphasis, the students have to actually look at data in certain areas. But it's just fascinating because these students have a lot more statistics and even a probability course than the average computing student. We look in companies where they hire data scientists, and they often hire people with computing degrees who've had almost no statistics. So I think that data science as a field of education really presents an opportunity for us to kind of rebuild the way we teach people how to deal with data. Terry.
Yeah. Well, no, I think that statistical reasoning is too important to be left to the statistics courses. I think that this is something that the general public needs to know about. And I'll give you one example. I was talking to Pietro Perona at Caltech recently. He's in computer vision. And he said that he and his wife were worried about some tests, the adverse effects of the tests on their child. They just had a child and they're testing it. And, he's really concerned, but then he did a calculation. What's the probability that, I'm going to die in a car accident on the way to the test? And it turns out that that's much higher. But no, most people don't actually do these calculations. They don't understand. And when there's a plane crash, they immediately assume that, oh, planes are dangerous. And I think this is a problem that really permeates all of society in terms of decisions that politicians are making. I think we have a real job ahead of us to actually educate the whole public. Very important.
So people have been advocating.
I wanted to add my comments and a question for everyone, the panelists and the audience. So first of all, I completely agree with Jennifer in terms of the kinds of graduates that we want to produce should come out with both computational thinking and statistical thinking if they are data scientists. And I also agree with the importance of ethics. And the master's program at Columbia is heavy on both computer science and statistics and working with real world data. But with respect to what Terry said, what the question I was going to ask everyone is, should we not be thinking about what we should be teaching at the K through 12 level in terms of working with data? And this, people know me for promoting computer science at the K through 12 level, but I do think that just basic probability and statistics and working with data also needs to be done. There's, of course, no room in the K through 12 curriculum. So it's not good enough to just say we need to do this. We would need to figure out how it's even feasible to do this. But I completely agree with Terry when we read newspaper articles and they highlight the inadequacy of the general public to even analyze risk or even know what a probability is. And I think there's a lot of education that needs to happen. And I would like to see this data science community as helping in that education process. And maybe it's almost too late when we're talking about college students and graduate students, but for sure we should be making sure our graduates come out with statistical thinking and computational thinking.
Perhaps the way we have mathematical reasoning as a course, that we should have a reasoning with the data or statistical reasoning, both in high schools and maybe earlier. Yeah, Emmanuel?
Well, one radical suggestion that was made to me by Alfred Spector, many of you know him, is, and please, this is his radical suggestion, not mine, is that we shouldn't teach calculus to high school students anymore. We should teach data science, reasoning with data.
So I just want to say one thing. There's a mathematical reasoning class that everybody at Berkeley has to take. No particular one, but they need some mathematical reasoning. And we are putting together a data science class for that because I think that's just really important. I don't think you can be a member of the civil society anymore without having some idea how to interpret the data and the data-driven conclusions that are being thrown at you. And about high school, when my stepson was living with us, 20 years ago, he wanted to take calculus in high school. And I said, oh, there's a probability and statistics class. I want you to take that instead. And he told me at the time, wow, this is amazing. I can use this everywhere. So I totally agree with you. You can't be literate anymore without some probability and statistics.
I'm so glad to hear this. It tailors back to really a question I'm interested in. I wanted to pause to you. And Terry, it's related to your work on Boltzmann machines and neural networks and how the neurons were inspired by human brain activity and understanding human brains. So it's also connected to interdisciplinary nature of data science. So how do we develop, where do you see data science challenges in terms of interplay with science? Maybe biology as a good example, but science should not be viewed as a receptor of data science, right? There should be some sort of collaboration and moving forward. So just wanted to open up the discussion. Please go ahead, Terry.
First, a small correction to your intro. You said that I was the president of the NeurIPS Foundation. I still am. And last December, for the last 30 years, and for the last year, we were online and we had 26,000 participants, just to give you an idea of the interest. And it's been going up 40% over the last 5 years. And at this rate, everybody in the world is going to come to the meeting in a couple of decades. That's clearly not going to happen. But you see this happening at your university, all these data science institutes. There's a tremendous, I think, really exciting, exploration going on now, and statistics are at the base of it. This is really what's pushing it. And by the way, Leo Breiman was one of the very first people. He came to the very first, back then, the NIPS meeting, which he was a stalwart in terms of seeing that this is going to have a big future. But to go to your question about bio-inspired sources, we're just scratching the surface, and I'll just give one example. There was a very influential Go match that took place between AlphaGo and the world Go champion, Kejie. This was 2017, and DeepMind. And it wasn't just that he won 3 out of 3. It was that it was extremely, the moves that were being made had never been made by any human before, and they were it was in a different class. It had been creative. Now that was not just deep learning. It was also another learning algorithm called temporal difference learning, which is a model for the basal ganglia. It's another part of the brain that has to make decisions, sequences of decisions to reach future goals, future rewards. And it's really the coupling between these two algorithms that in humans, which is much more in terms of the sophistication and large numbers and so forth, gives us our, ultimately our intelligent behavior has to come from all of the interactions between these neurons. But there's many other parts of the brain, hundreds of parts of the brain that are also contributing important pieces of information about confidence. There are neuromodulatory systems that tell us, this is how likely is this decision going to be risky or not, and so I think that there's a tremendous amount that can still be done in terms of being able to enrich, and so now just to go to the science part. So I'm a neuroscientist, a computational neuroscientist, and we're trying to understand, and you mentioned before the Obama Brain Initiative on the Brain Initiative, which was has been halfway through the 10 years, and it's been extremely successful. We went from just being able to record 1 or 2 neurons at the same time to now, just last week, it's up to 1 million. And it's completely transformed how we think about how different parts of the cortex interact with each other, and how decisions are made. And it's I'm teaching a graduate course, and it's like all over. We're just recreating the whole approach. Now, here's the point that I want to make, which is that how do you analyze 1 million neurons? The old days you could do each one by hand, but machine learning. It turns out that statistical techniques that you can scale up are being used by neuroscientists to analyze brain imaging data of single unit recordings from single neurons, recordings from epilepsy patients, and this is vastly improving our knowledge of how the brain works. So there's this incredible opportunity now because of the fact that so many of the algorithms that now have been imported are inspired by the brain. Now they can come back and help take us to the next step. So I think that this interaction is going to be very, in the future, moving forward, is going to be very important. And we need people in between who know enough about the brain to be able to come up with new algorithms and vice versa. And by the way, it's not just neuroscience that's benefiting, all of science. I mean, it's incredible how many areas of science, physics, chemistry. You probably heard the news that, protein folding, which is one of the most holy grails in all of biology. How do you go from the primary amino acid sequence to the tertiary three-dimensional structure of a protein, which is how it functions? And again, it was DeepMind, AlphaFold. It's amazing. It's now reached the point where it's as accurate as X-ray crystallography. And this is astonishing. I never thought in my lifetime this would ever happen, because the complexity of that problem was just enormous. And it was done with the kinds of algorithms now that are coming out of our community. So this is a really exciting time right now for everybody. And this is, I really think that we're on the cusp of something really important.
Indeed, and perhaps this is the place where data science and not just statistics can nurture that interdisciplinarity and different kind of learning, right, and research.
Yeah, and by the way, I think we heard earlier that how many 18 different departments. I mean, this is affecting humanities. It's affecting social studies and politics. It's the political use case is a very important one too. This is anyone who has data now is really going to take advantage of that through these tools and techniques. And that also means that we have to be extra careful about making sure that it's not misused. And the misuses have just begun. We have unintended consequences that are not even imagined, that we're going to have to be very patrol and make sure that we keep our colleagues honest about how they use the tools.
Yeah. So Emmanuel.
Yeah. So people have talked about ethics, and so this is another connection with the rest of the world that I think is extremely important. What I'm expecting as a data scientist from this interaction with ethicists is I would like to have a dialogue with ethicists so that they can inform us about what to research and perhaps also what not to research. Let me give you an example. I see papers published in machine learning that, you have like cars and they drive through neighborhoods and they match voter registration with the cars they see on the streets. And, you have headlines in the newspapers where, Democrats tend to have Priuses and Republicans tend to have, I don't know, this is dangerous. I mean, this is dangerous. First of all, this correlation is not causation. Not number one, it's not the type of car you drive does not determine who you are. But should we actually, and if anything, it's gonna, we're a fractured society. If anything, it's gonna divide us more. And so, other types of, things like I see in my own work, there's a lot of work because we have the data in statistical genetics, and I work a bit in statistical genetics with experts, not on my own. People are researching the genes that could explain sexual orientation. Should we do this? Because, if we find indeed mutations, that explains what are we supposed to do about this? I don't know. I'm not an ethicist. I've not thought about this question, but I understand why I want to find genes associated with certain form of cancers. I want to do gene therapy. But now if I find genes that explain social, what do I want to do? I want gene therapy. It's not clear. So to me, the dialogue with ethicists is very important because they can inform, they can help me study what's important versus not. And maybe there are research topics we should just keep off. And that's what I want from my ethicist colleagues to tell me. What is it worth pursuing, and perhaps what is not worth pursuing?
Very good. Sorry, Jennifer. We have 4 minutes left, and we have a very interesting. It's a lively and wonderful discussion, but we're limited with time. But the audience has asked a really good question, I think. What is the role in the research between academia and industry in data science? And perhaps Jeanette and Jennifer to begin with this question. Yeah, so whoever wants first.
Well, I'll start, but Jennifer can say more. You know, when you know, when I just joined Microsoft, the phenomenal demo of DNNs doing speech recognition and speech synthesis and so on was given by Rick Rashid, our former boss. And that's when I knew that industry had an advantage over academia. They have the data and they have the compute power. Everyone has the algorithms, but industry has the advantage. And right now, the more data, the better the model, or I'm simplifying. And not only does industry have compute power, basically it's infinite compute power, but they can afford GPU clusters in a way that academia would never be able to afford. So, you know, when Jennifer and I were both at Microsoft together, it was clear to me that in certain areas of machine learning and data science and AI, industry was far ahead of academia. In fact, I remember talking to a friend of mine at Carnegie Mellon in NLP. I met him in the airport and I was still at Microsoft. And I said, what are you working on? He's, I'm working on those problems that industry couldn't care less about because what it was left for academics to work on. So I'll be quiet, but I you know, I think it's a challenge for academics to figure out, this is one of the reasons I wrote that little article, was to say there are still deep scientific questions for this field to pursue and answer that will take the long-term thinking and the academic environment to pursue. That industry does not have the time. First of all, industry is all competing with each other at this point. So industry doesn't have the time to do the long-term research that academia, in fact, is responsible for doing. So Jennifer, I'll let you speak.
Thank you.
Well, I just agree that there's so much more data in industry, to the extent that we can have partnerships between industry and academia. And there are many areas where we can have those partnerships. I think it's really, really important to do so, and industry often wants to have those partnerships. I think there are also issues, ethical issues when things get in the way of the business models of industry, which we can do much more easily in academia. Terry has something to finish up with here.
Yeah, so look, I was trained as a physicist, I have a PhD in physics from Princeton. A lot of the, friends I had back then are working on the LHC, the Large Hadron Collider in CERN. And, it's not something that, any lab can have their own collider, right? And because there are some questions that only, you have to scale it up. And that's something that requires nations to support. And I think there's nothing wrong with having some companies have the compute power available that they can begin to explore the outer limits of where you can go and what the scaling laws look like. And I'm not saying that should replace what's going on in academia. I agree completely that we have a lot of other issues and advantages that perhaps more time but I think it's going to evolve in the way physics did in terms of having a multi-tier system.
I want to put in a plug because people know that I served at the National Science Foundation and Terry being the Obama brain person. What Terry pointed out was very important with respect to the role of federal government and federal investments in basic research. It's an ecosystem, academia, industry, and government. We all need each other. LHC would not be without the different countries participating in building the one instrument. And so just putting in the plug for the role of the federal government.
Absolutely, absolutely.
Emmanuel, do you have...
I work a bit in industry, half time, 10% of the time. I completely agree with the assessment that was made that the compute power and even the ease of data science tools is far better in industry than it is at Stanford. We're so far behind at Stanford in computing platforms and so on. I think a plug for academia is there's a mistrust in institutions in the country, but I would say that universities fare better than most institutions. The public is still quite trustful of universities, and it's less trustful of giant tech companies like Facebook and Google and even perhaps Microsoft. And so we need to find a way to leverage this public trust to do big data work, because there's still quite a fair amount of public trust in, at least according to a report I've read, in universities. And so, let's put this trust to good use, because this is where we have an advantage.
Yeah, I completely agree. It's the interdisciplinary now between academia and industry that needs to happen. And kind of funny, Terry, that you mentioned CERN. I'm no physicist by any means, but my data science course on reasoning used CERN data as a final project. So that was fun.
I want to mention one more thing. Universities educate the next generation. They educate everybody who is going to go out into industry and to government. And we have a huge role in doing that in such a way that people use these platforms and these technologies for the good of society.
Wonderful. Great note to finish off our panel. Thank you very much for your time. It was lovely. It was good to see you all. Stay safe and healthy.
I want to thank Yelena for
Bye-bye. Thank you, everyone. Nice seeing everyone. Bye-bye.
Bye-bye.
Thanks, Yelena.
I want to thank Yelena for organizing this very thought-provoking panel with our very distinguished guests, Terry, Jennifer, Jeanette, Emmanuel. Thank you so much.
Thank you,
and for the breakout, we will be continuing to broadcast live. So please use the breakout rooms. We will have 10 breakout rooms for private discussion, and we will resume again at 2 with a very interesting panel discussion on COVID. Thank you.
At the Halajulu Data Science Institute, we're addressing and solving real-world problems through laying the groundwork for the scientific foundations in the field of data science. We are developing new, innovative methods and infrastructure, working with faculty, students, alumni, and industry partners to leverage interdisciplinary knowledge to train and prepare the future leaders of data science.
This is April 21st. It has been more than a month now since we have been in this great pause, working from home.
What was only supposed to be a month or two has now turned into over a year of working remotely off campus and virtual learning. But that didn't hinder our success, our impact, as we celebrate our 3rd anniversary at UC San Diego. We are proud to celebrate our inaugural graduating class of 75 students who now join the ranks of UC San Diego alumni. We awarded 29 undergraduate scholarships and learned from 27 senior capstone projects. Of our class of 2020, 44% of our graduates are now working within various industries, while 23% are pursuing further degrees and research opportunities. In addition, we welcomed 196 new data science students destined for the class of 2024. While leading our students through distance and remote learning opportunities, our faculty sponsored and participated in nearly 60 academic symposia and related events throughout the year. HDSI nearly doubled our faculty since our founding, forming a core group of 11 full-time faculty and 13 jointly appointed faculty, while also expanding our faculty council and faculty fellows. HDSI continued a strong industry partnership alliance program, now with 11 active partners and over 60 stakeholders. We welcomed 3 new partners, Epicor, Dexcom, and Thermo Fisher. And 26 data science students were mentored directly by industry leaders in our senior capstone projects. For example, our Deloitte mentorship program connected 14 leaders from Deloitte directly with 15 of our data science students, while our partnership with Intel across several projects involved 9 data science students, 6 HDSI faculty, and 11 mentors from Intel. We celebrated the launch of HDSI Career Services. In less than a year, Career Services hosted nearly 20 remote events, trainings, and programs, providing outreach, resources, networking opportunities, and support to our seniors, alumni, and industry partners. In a year off campus, HDSI also sponsored many large-scale programs throughout the year, including our Senior Capstone Showcase, Socially Distanced Triton 5K, Senior Orientation and Senior Open House, Data Science Talent Day, and many other events. We thank each of you who have been part of our success as we celebrate our 3rd anniversary. To our faculty, students, staff, alumni, industry partners, and UC San Diego collaborators, thank you for an amazing year.
I could see Bobby sweating again on the video. Maybe something else would go wrong, but looks like we survived. Okay, it's all right. Rob, you have your panel with you? The panelists?
I hope so. You tell me.
Okay, let's see. I see Ilya. Let's see.
I saw Natasha there.
Hi, everybody.
Good to see you, Natasha. We are in good times. At least the big bump we had on cases has come down significantly. I see Cheryl there. Excellent. All right, Cheryl joins. Excellent. Good to see you.
Hello, good to see you as well.
Mhm. So we are missing Kim. We had a great panel in the just before lunch that crossed data science, social sciences, ethics, fairness, more than ethics, but fairness.
Does sound really good.
Mm.
Halajulu Data Science Institute, we're addressing and solving real-world problems through laying the groundwork for the scientific foundations in the field of data science. We are developing new, innovative methods and infrastructure, working with faculty, students, alumni, and industry partners to leverage interdisciplinary knowledge to train and prepare the future leaders of data science.
This is April 21st. It has been more than a month now since we have been in this great pause, working from home.
What was only supposed to be a month or two has now turned into over a year of working remotely off campus and virtual learning. But that didn't hinder our success, our impact, as we celebrate our 3rd anniversary at UC San Diego. We are proud to celebrate our inaugural graduating class of 75 students who now join the ranks of UC San Diego alumni. We awarded 29 undergraduate scholarships and learned from 27 senior capstone projects. Of our class of 2020, 44% of our graduates are now working within various industries, while 23% are pursuing further degrees and research opportunities. In addition, we welcomed 196 new data science students destined for the class of 2024. While leading our students through distance and remote learning opportunities, our faculty sponsored and participated in nearly 60 academic symposia and related events throughout the year. HDSI nearly doubled our faculty since our founding, forming a core group of 11 full-time faculty and 13 jointly appointed faculty, while also expanding our faculty council and faculty fellows. HDSI continued a strong industry partnership alliance program, now with 11 active partners and over 60 stakeholders. We welcomed 3 new partners, Epicor, Dexcom, and Thermo Fisher. And 26 data science students were mentored directly by industry leaders in our senior capstone projects. For example, our Deloitte mentorship program connected 14 leaders from Deloitte directly with 15 of our data science students, while our partnership with Intel across several projects involved 9 data science students, 6 HDSI faculty, and 11 mentors from Intel. We celebrated the launch of HDSI Career Services. In less than a year, Career Services hosted nearly 20 remote events, trainings, and programs, providing outreach, resources, networking opportunities, and support to our seniors, alumni, and industry partners. In a year off campus, HDSI also sponsored many large-scale programs throughout the year, including our Senior Capstone Showcase, Socially Distanced Triton 5K, Senior Orientation and Senior Open House, Data Science Talent Day, and many other events. We thank each of you who have been part of our success as we celebrate our 3rd anniversary. To our faculty, students, staff, alumni, industry partners, and UC San Diego collaborators, thank you for an amazing year.
All right. Welcome back to the afternoon sessions. It is my pleasure to introduce our moderator, Rob Knight, to conduct this panel on COVID. Rob has a very lengthy resume, but I'll just say briefly, one of my greatest accomplishments as a chair of computer science was to attract Rob to UCSD, who's a professor of pediatrics, computer science, HDSI, and director of Center for Microbiome Innovation. So Rob, please take it from here.
Thank you, Rajesh, for that very kind introduction, and thank you for inviting us to participate as a panel on this very timely topic of COVID and what UC San Diego is doing to uniquely combat it, and what role data science plays in all of this. This was originally billed as a fireside chat, but we figured the whole world is on fire at the moment, at least metaphorically. So that's our backdrop. Just to introduce the panelists that we have tackling this problem from different perspectives. We have several of the key figures in Return to Learn and then across campus, pushing this work with COVID into the environment and into interaction with county and the public schools, so that we can keep not just our institutions safe, but also broaden the impact of our work to the community more generally. So introducing the other panelists, Cheryl Anderson is our founding dean of the brand new Herbert Wertheim School of Public Health, and she's the director of the UCSD Center of Excellence in Health Promotion and Equity, as well as being a fellow of the American Heart Association, where she chairs the Nutrition Committee, and she's also been elected to the National Academy of Medicine, and she's really an expert on diet, health, and on health equity. Kim Prather is a distinguished chair in atmospheric chemistry and a distinguished professor in the Scripps Institution of Oceanography and the Department of Chemistry. She's the director of an ocean aerosol center called CASE, and she's the first female member of the National Academy of Engineering to be elected from UCSD, and was also recently elected to the National Academy of Sciences. And for a long time, she's been making waves in her career, quite literally, where she has this wave flume at Scripps, where she recaptures the properties of ocean spray to see what gets launched out into the environment. And more recently, she's been applying this work to understand what happens with SARS-CoV-2 and can it get from the environment back into the human body. Natasha Martin is another of the key players in Return to Learn, providing the modeling component that's helping informing all of the work that we're doing to keep us safe on campus. So Natasha is an associate professor of medicine. She's educated at Oxford and Stanford, and she's an expert at modeling in HIV and HCV. And she's been applying these skills to address the critical COVID pandemic at present. And then Ilya Zaslavsky is the director of the Spatial Information Systems Lab at HDSI, the San Diego Supercomputer Center, which is the building where HDSI is currently co-located. And Ilya is an expert on GIS modeling and understanding the spatial distribution of different phenomena. He's been on weekly calls with county, as actually have Cheryl, Natasha, and myself. But Ilya in particular has been applying his modeling skills and spatial information skills together with county to understand the distribution of the burden of disease of COVID in our community, and to help county figure out where to target testing and now increasingly interventions, including vaccination and others. So, I thought I'd throw out some questions to the group to get started with, and then we'll also broaden this discussion to include the audience later in the panel. And so initially, one really pressing question with this pandemic, as has been true for many other pandemics, is trying to figure out how the virus is transmitted. So, for example, how can data science inform the inform our understanding of the transmission rates of SARS-CoV-2 and also the transmission modes of this virus. And in particular, there's been a lot of debate about whether the virus is airborne or not. Kim, I wonder if you'd like to start the discussion by sharing your thoughts on that, based on your extensive expertise with aerosol chemistry. And I think your microphone is muted right now.
Yes, thank you. Unmute, like, should I not know this by now? But yeah, I'm happy to do that. And I was told that I could share one slide. So I'm going to pull up one. I might go to more, but I'll just stop here. Anyway, so yeah, I've spent the last nearly year. How can we confirm, that this virus is getting around? Let me put this on. Hold on, sorry. Oh shoot, sorry. Hold on. All right. So yeah, so a big question has been, historically, respiratory viruses, the focus of the medical community has been on droplets and how droplets affect us and how to protect against droplets. And so one of the big things that's come out of this pandemic is how this virus is actually in the air. And there's just no question. All evidence points to this virus being in the air, particularly in aerosols, which is what I study. And so, we think about direct contact, indirect contact, droplets, like someone sneezes in your face, in aerosols. And so, one of the questions that you and I talked about was, how do you, how could data science, sort these different modes of transmission out? And so one of the things that has come out of this pandemic, and it drives me crazy, honestly, is we use this 6-foot rule. We say it won't go beyond 6 feet. And if you have, less than, 15 minutes, you're fine. That is, where did that come from? And so I think this is a place where data science could really make a difference in terms of, expanding our understanding of, what happens if you made it a bigger distance, a shorter distance. You could take environmental conditions in a room. You could make it longer, shorter times and see if you capture more people. The bottom line is I really think there's a lot of room for improvement in terms of, in general, how respiratory viruses get around. We sent a letter to the Biden administration this last week. It is in the air. How do we show that? And it is, there is massive data science data sets that we could use, we could mine and do so much better on this problem. So I'll leave it at that.
So thank you. That's a fascinating perspective. And Cheryl, and I don't know how you do this, but on top of everything else, you're leading the contact tracing component of Return to Learn. How do you think these kinds of ideas would tie into what we need to do for contact tracing, either on campus or more broadly with the COVID effort?
Yeah, so, as Kim just mentioned, we, in contact tracing, we're thinking about how do we get people to not inadvertently pass this virus around, right? It's highly contagious, and we want to ensure that we let people who could possibly be at risk know as soon as possible about whether or not they've been in contact with someone who's been infected. And, to Kim's point, the focus for us is usually on how much time you've been around a person within a certain distance. And that distance right now by CDC guidelines is within 6 feet. So I am waiting so eagerly for Dr. Prather's data to get to the CDC so that we can make this adjustment as necessary. But for right now, we're living with what I think are maybe 20-year-old data around how viruses typically get transmitted. That said, I want to just re-emphasize the point that was already made about how data science can help us in this space. So, we not only need to think about individuals who have infection and could pass it on to others, but we need to think about those people who have been in close contact with them and whether or not the close contacts could also be at high risk for transmission, because then you get this exponential increase in the virus's activities. And so again, the use of data science to help us understand those potential pathways can be really impactful. And then Rob, with your team, we've been working to better understand what we know about outbreaks, not only identifying them, but also mitigating them. And so introducing the idea of whole genome sequencing, which is something that your laboratory helps us to get started. It gets confirmed, and then we're able to better understand, as we see contacts clustered together, are those contacts likely sharing similar strains, and whether or not the potential impact of those strains vary in any way. So I'm really excited about this conversation that we're having today regarding data science, because it may all seem quite straightforward. However, our ability to be good interveners, to identify the problem well, to understand how it moves through the population, requires us to have very strong data, big data, in many instances, so that we can better work, whether it's here on the campus or within the general region.
Great, thank you, Cheryl, and thanks for bringing up genome sequencing. So one thing we're doing now at UCSD at an unprecedented scale is sequencing the genome of SARS-CoV-2 from clinical remnant samples in our clinical labs, including the CARM, which is the clinical lab that's been running for decades, and the new Excite clinical lab that's dedicated to COVID testing and COVID sequencing, and supported by Return to Learn, as well as sequencing out of the wastewater all across campus. So there's these samplers all over campus that are pulling wastewater every day. And with Kim, looking at samples in the Tijuana River, in the ocean spray, in the estuary zone, and so on. And I think integrating the human and environmental sides of this is going to be really important. Natasha, I was wondering, one thing that's really characterized Return to Learn and the ability to pull all these pieces together has been the amazing and I think unique collaborative cross-campus nature of the program. And I was wondering if you wanted to speak to that collaborative nature, both with what's going on campus and what's going on with the vendors and partners in various companies that are helping us accomplish this unique one-of-a-kind program.
Yeah, sure. Happy to talk about it. And maybe I will share a little slide that I think encapsulates it nicely. Many of you know about our Return to Learn program having these three pillars: risk mitigation, viral detection, and public health intervention, and those being very interdependent and having an adaptive approach. But what I wanted to talk a little bit about, back to Rob, your question in terms of the sort of multiple groups that are coming together to feed into a data-driven approach in terms of the Return to Learn program, is thinking about all the pieces of data that we are accumulating and reviewing on a daily basis to try to inform our decisions. So thinking back to those three pillars, we have groups that are obviously thinking and focusing on our traditional public health risk mitigation efforts, so masking, social distancing, sanitation, and ventilation. So for example, Rajesh's team has developed very sophisticated simulation models to look at airflow in buildings and help us understand ventilation systems and how we can think about repopulating our classroom and research settings, but making that as safe as possible. So that quantitative data helps us understand our approach on campus. We've done some simulation modeling to understand the effect of de-densification of housing, and thinking about that on campus. And then of course, in our middle pillar of viral monitoring, there's many teams that are involved in the asymptomatic and symptomatic testing, both at the CALM lab and the Excite lab, that are working to increase both the volume of testing, but also how easy it is, right? We've just expanded all these vending machines where students and campus employees can pick up these tests. And so we have a huge implementation program in terms of getting those tests out, but also then the data analytics program in terms of understanding testing, test positivity, and case rates, which again, we monitor on a daily basis. We collect and analyze symptom screening data in terms of whether people are reporting symptoms. And of course, the wastewater and surface monitoring efforts led by Rob Knight's and Smriti Karthikeyan's teams in terms of monitoring the sewage coming from our residential and non-residential buildings. We now have over 110 wastewater monitors covering over 300 buildings on campus. Those samples are collected every day. And so we analyze the data and have built out really, the data analytics teams have built out really incredible visualization systems in terms of the connectivity of those sewers, how they connect to buildings, so we can identify which potential buildings are sources, and then recommend that individuals that are living and working in those buildings get tested. And so that helps us identify outbreaks at the earliest stages, and it appears to be extremely sensitive, right? We have one, maybe in a building of several hundred students can identify one asymptomatic infection. The viral sequencing efforts, both at CALM and Excite, are really important. They help us, we get the sequence data, they allow us to track the variants, but they also allow us to understand potential transmission clusters. If we see a cluster of infections within a specific residence, but we look at the sequence data and see that they are unrelated, then we can be fairly confident that that was not a result of transmission on campus. And so, we're using that information in a lot of different ways and overlaying them. And I think the data science teams have been working very hard to try to incorporate and integrate these pieces of data so we can understand, for example, if we see a positive wastewater signal, do we find a matching sequence among an individual? Have we likely identified the individual that was the source of that sequence? And what do we see in terms of variance? Which I think will be increasingly important moving forward. Yep.
Sorry, go ahead.
No, just the last thing is and then of course we're incorporating modeling in terms of forecasting at the county level and integrating that data and trying to keep an eye on what's going on both in the community as well as what's going on campus, so that we can adjust our approach as we see, for example, the expansion of variants or cases in the community and potentially that reflected in our on-campus populations.
Thanks, Natasha. That's wonderful, and I think it's important to reinforce the scale of this. Like, all of New York City has only 15 of those wastewater samplers in their sampling program, whereas I think I heard you say that on campus we already have over 100 that are active and pulling data every single day right now. And to do this, it's been just amazing. The collaboration between Health IT, Campus IT, the San Diego Supercomputer Center, colleagues in computer science and engineering in the Herbert Wertheim School of Public Health, in the Center for Computational Biology and Bioinformatics, and probably many other organizations that I'm shamefully neglecting here, just to be able to collect and process all of this data and turn it into a consistent view. So coming back to the question about aerosols and transmissibility, Ilya, I know you've been doing a lot of work mapping where COVID is in San Diego County. Does any of the geospatial data you have, could that be used to inform that question about transmission modes? And could you also speak more broadly about the role of GIS in responding to this and to other pandemics?
Yeah, thanks, Rob. We're living through a very interesting time where there's a lot of data and people are very willing and to share data widely and quickly. At the same time, there is not enough data for what we need. Even some key things, such as what we can map easily, is counts of cases from different areas. They reflect the level of infection only partially, because many infections are mild and not really reported. And it depends on testing, it depends on who is being tested. There are lots of factors that make us question what are actually the numbers that we're trying to explain. And not to mention when we try to focus on specific population groups. So for example, in our school modeling project that I'm going to talk about a little bit more, we are trying to build simulations for COVID-19 transmission in schools. When you try to build this model, you want to look for parameters that have been reported by studies, and they're organized in several projects on the web where you can pick up the parameters. Most of them reflect general population. Out of 1,000 parameters or so that you can find, only a dozen would reflect school age, school age population. So what data science can contribute and what GIS can contribute is in forecast models and generally in modeling. Of course, models are all incorrect, but some of them can be useful. And when we're talking about useful, I need to mention Natasha Martin's work. It's really amazing because it shows how COVID, more or less real COVID numbers can be reconstructed and forecast for the county and for the state. I know how comprehensive and difficult it is because we actually try to do that with students based on local models. We take, say, infection rates by zip codes and try to explain them based on health indicators, social economic factors, and a bunch of other factors for that zip code. And what happens is that we do this in June, and it's like overshoot for all zip codes. Then another month it's undershoot. So there are lots of other factors that we haven't included in the model, such as the general attitude in the population as to whether they should stay safe, and then this feeling kind of relaxed. Not to mention regulations that come from the county, from the state. So this is a very difficult work, and this is what data science can contribute a lot. I guess I will share my slide on the next round of questions.
Please do.
Do you want me to continue or?
Oh, well, do you want to share your slide now, or do you want to share it with one of the later questions?
With one of the later, yes.
Okay, sure. Well, following up on that question, I was wondering if you'd like to, Ilya, comment on what the role of data science is in limiting and tracking viral spread, especially in terms of identifying vulnerable populations and individuals. And I know this is something that's come up as especially important in working with the public schools, where there's tremendous disparities in resources, in things like whether the students and parents associated with the school are documented, all kinds of other things that affect access to healthcare, to COVID testing, to vaccination, and so on. And what is your thoughts? What are your thoughts about how data science can address those kinds of issues?
Yeah, that's a very good question. And indeed, there are many types of vulnerable populations. Can you see my screen? Because it's for some reason.
Yes, it's just come up now.
Right. So there are vulnerable populations that are kind of understood through more or less traditional divide lines, such as based on social, economic, and demographic characteristics, on ethnicity. Do you see it or not?
I'm afraid it's disappeared again. We saw it briefly, and then it's just showing black with a couple of gray bars.
Okay. Sorry about that. Can you hear me, see me?
We can hear you and see you. We just can't see your screen.
Okay, I'll try to switch to, there's one monitor disconnected. Right, but there are certainly, all these factors, social, economic, and demographic, are strongly intertwined, and that makes it difficult to define such populations in operational fashion. So for example, there is a higher rate of infection among Hispanic populations, that Hispanic communities in Southeast San Diego and in areas like this, such as Escondida. And there are many reasons to that, not only lower income and lower kind of opportunities to get healthcare, but also in Southern California, housing prices are very high. As a result, lower income people tend to have multi-generational households, so children and parents and grandparents all live together, and this is a strong factor in transmission. Then, of course, we can think of non-traditional vulnerable population. I'm sure you have seen results of recent polls saying that the divide now in terms of attitude to vaccination is along party lines. There are about 4 times more Republicans who don't want to get vaccinated than Democrats. And this gap actually gets wider as polls show. And I don't want to say anything about the the reason for these ideas or political beliefs. That's a separate story. But it's definitely a vulnerable group that would require some specific public health measures to address the needs.
Great, thanks, Ilya. Now, Cheryl, I know you've thought a tremendous amount about health disparities in other contexts, especially cardiovascular disease, but also infectious diseases. Do you see any lessons from those other settings that apply nicely to COVID, or and are there any aspects where COVID is really unique with respect to health disparities?
Yeah, thank you for that question, Rob. One of the things that COVID-19 did was give us a master class in how to think about health equity, and it exposed some of the ongoing challenges that we've had in this country and in some other parts of the world also. Now, what we saw initially as the pandemic became more obvious were these really incredible geospatial differences in COVID-19, largely driven by, again, great data science. And we, over time, began to kind of dive into some of our own regional differences in the country. We were seeing initially, things happening on the coast where there was lots of travel. But then as the infection began to spread, we saw that within communities where we already see a higher burden of cardiovascular disease, the #1 killer, in the country and across the world, cancers, obesity, diabetes, hypertension. If you take those maps, those data maps, and you overlay them onto how we were experiencing COVID-19, it was incredible, right? It looked as though you were talking about any of those other conditions. What then became important was, of course, the mitigation strategies that we were going to try and use, because these chronic diseases will require will require a chronic, kind of a more chronic oriented solution. And here we are in a pandemic with no time to waste and an urgency to really try and address it. So we in San Diego, I think, took a very nice approach, which was through the Healthy Place Index, which again is driven by great data science. We were able to map where we would send testing resources, and UC San Diego, the putting together of the Excite Lab was important in this space, because the more testing capacity that we had here, the more opportunity for the county to leverage having tests available and to bring testing sites into some of the neighborhoods where we saw this virus and the infections being disproportionately borne out. So that was one thing that we saw that we needed to do, and I think we effectively got testing into communities that were in need. Once we test, we have the ability to identify that the virus is there, and we can act accordingly using some traditional public health strategies: isolation, quarantining, contact tracing, and hopefully preventing spread. So that is that's one piece of the disparity. The other thing that's more proximal now is how we are experiencing the vaccine rollout and the vaccine uptake. And so fortunately in San Diego, our latest data, surveys data show that 80% of the residents in San Diego would like to get the vaccine. So the struggle here isn't so much, I am hesitant and I don't want to take it, as much as I'd like to get it, please get it to me. How can I get to the vaccine? And it is in many ways a miracle if you get a vaccine in your arm right now, and you can imagine that some of the ways that we've been working at this helps us to do it quickly, but it might leave some communities behind, communities who aren't necessarily well suited with technology, individuals who don't necessarily have access and transport. And so what I'm seeing us do, particularly here at UC San Diego, is mount efforts to meet people where they are, to try and bridge this digital divide, and to, as best as we can, really understand what are some of the upstream factors that impact this infection and disease disproportionately impacting others. And so, you know, this is a space where long beyond COVID-19, we're going to need to manage through some very tough, deep-seated historical issues, systemic racism, which plays itself out in many ways in our legal system, in our social systems, in our politics. We'll need to deal with structural issues. Think about how we plan cities, where people live. Why is it that it constantly happens that your zip code is determining your life expectancy and the way you experience conditions? So COVID, if anything, I think it really reinforced what many of us who've been working in the space of health disparities and health equities have been trying to bring to common knowledge. And I hear now more sensibilities around this issue because of COVID than you would have heard even 5 years ago. And so I'm really excited about what we here at UC San Diego have done around testing and vaccine rollouts, et cetera, to really try and bridge some of this divide. But as you know, there's a lot of work yet to be done. When you look at current county data, I just saw Dr. Happy Araneta from the School of Medicine and the School of Public Health present these recently. We see that the rate of vaccine uptake is lower than what you would anticipate given the demographics of San Diego in communities of color. And again, not because necessarily people don't want to get the vaccine, but because there's structural things there that are getting in the way of people being able to do so. So I really look forward to us trying to solve these issues. And our new School of Public Health is deeply sort of interested and well positioned to try and make some headway on this.
Thanks, Cheryl. That was fascinating, and I agree completely about some of the concerns around the current vaccination strategy, and I'm really glad that the plan is to meet people where they are. So the New York Times just ran an article expressing concern about super sites like the vaccination super site in Connecticut, but at the same time, things like the Petco site and the Remax site, while on the one hand, they've done this amazing heroic effort of vaccinating over 100,000 people in our community already. On the other hand, you have to be motivated enough to sign up on the website, be able to navigate that technology, be able to have the resources to get yourself to the vaccination site. And I can certainly see that exacerbating rather than ameliorating health inequalities. Now I want to come back to something fascinating that you said earlier in your answer.
Rob, one quick thing though, there are quite a few questions though, both on the chat and so go ahead and let's open that up also. Go ahead, please.
Sure, absolutely. I'll come back to the chat in just a moment, but you said something fascinating earlier in your answer, that if you take the map of cardiovascular disease, diabetes, other chronic diseases, and then superimpose COVID on top of that, it's exactly the same map. And so that makes me wonder whether there's a really important role in responding not just to this pandemic, but also making ourselves resilient to future pandemics in addressing those structural inequalities in society and in the environments where people live. Would you agree with that?
Yeah, I would agree completely with that. It is how we manage COVID-19 can be a really nice template for what we can do moving forward, because what we'd previously been doing in the space of health disparities and health equity was clearly not enough. And it left us with a real, it left us vulnerable to how COVID-19 really ravaged many of these communities. And so, once you know better, you must do better. And having seen what happened in this instance makes me, to your point, very, very convicted about us taking some of these lessons and making sure we don't have, because there will be another pandemic, making sure we're in better shape the next time.
Great, wonderful, and I think an important part of that could be negotiating the hurdles that currently exist in combining human and environmental research and putting all these pieces of the puzzle together. So Ilya would like to show his slide again and comment on that. And while he's setting that up, there's some questions in the chat that I'd like to go over. So one question for Ilya, just while you're doing the screen sharing, does this mean that we're ready to reopen the schools now, or are there additional things that we need to do before we could consider such reopening? Ilya, your microphone is muted.
That's a very interesting question, and of course there are different opinions and different answers to that. Of course, parents would very much like school to open, and children would.
Yeah, speaking as a parent, I'm certainly on board with that.
Right. At the same time, it would make sense to do it when it is safe, and teachers are very much concerned about potential exposure, because some modern studies show that likelihood for teachers to get infected is pretty high. The same type of sentiment is among school bus drivers that we recently talked with and got some data about school routes from. When you look at aerodynamics of airflows within a bus, it typically goes from the back of the bus to the front. And so as they pick up students from across San Diego, this can happen from areas that have pretty high rate of infection. As a result, and sometimes students spend an hour on the bus. So they are obviously concerned about their own health. So there are certainly ways to try to mitigate these concerns and keeping all windows open, having social distancing on the bus, and that would alleviate the potential infection. But this is where the debate is. What kind of measures we can propose to teachers and to school administrators and to San Diego Unified Transportation, so that they would be comfortable doing that. What I wanted to show quickly is a slide that shows some of our work when we try to analyze potential COVID-19 transmission in schools. And I should say that this entire topic came about because I taught DSC 170 spatial data science class in winter of this year. So we started this semester, that quarter, kind of looking at the Johns Hopkins dashboard, and that all looked quite remote. And then suddenly we have to cancel last week of classes, move it all to remote. And immediately after that, we decided to run a course, how to fight COVID with data science, out of which came a bunch of interesting projects. One of them was an attempt to map, and this is the dashboard that you see. It shows now infection rates for different zip codes and COVID-19 outbreaks in schools, and allows you to relate this to different social, demographic, health, and other indicators. Another thing is agent-based modeling of COVID-19 transmission in schools, where we take real school plans, and this is the chart that you see on the left. This is one of schools in San Diego County with the number of dots representing students and teachers, and we model how how likely the transmission can happen depending on the contacts between exposed students, between infected students and exposed, and through different types of activities that students go through as they go through their school day. As Kim mentioned, 6 feet is not a very useful number, because if the students run around during recess, or they sit at their desks in the classroom, or they have lunch together, or they sing, or they work in the gym, the potential transmission would be very different.
That's great. Thanks, Ilir. I'm just getting reminded that we do have to wrap up this panel because the Chancellor's on next, and we can't we can't delay that. But this is certainly a fascinating discussion. Kim, I know I just want to end with I know you've had a lot of thoughts about schools and what will be required in order to have them reopen safely. Can you give a very brief synopsis of that, and then we'll wrap up if that's okay.
Sure. Yeah, like minutes. So yeah, I've been advising a lot of schools, and I think, people ask me, can they reopen safely? And the answer is yes. We all want schools to reopen. Mental health is an issue. Number one, community transmission has to be lower. And that's what everybody as a community has to work on. But more importantly, there's a lot of really bad misinformation. It comes down to data analysis, data science, actually, where people have looked at the wrong data sets. They have looked at data that is largely dependent on kids testing, actually, when they have symptoms. Most of the time, kids don't have symptoms. So if you rely on those data sets, your answers are heavily biased against kids ever being the index case, kids carrying it home. So I'm a big believer that kids transmit, and opening schools at the wrong time can lead to another outbreak, which we don't want. UK is going to maybe show that to us again, sadly, soon. So, I think I look at these data all the time. At the end of the day, we can reopen safely. I will tell you, San Diego Unified, our biggest school district, has listened to everything I've said, and the focus is on cleaning the air, not just cleaning surfaces. This virus is spread through the air, and that is where our focus needs to be. And I think San Diego is way ahead of everybody else. So that was a 2-minute synopsis. Hope that was clear.
Okay, that's great. Thank you, Kim, and that's a very positive note to end on. So I'd just like to thank everyone on the panel for taking time out of your extraordinarily busy schedules to help HDSI celebrate its 3rd anniversary and talk about the unique role of data science in helping UC San Diego combat the COVID-19 pandemic, both on campus and in our community, and also the sheer breadth of skills organizations on campus and off campus that have had to come together in order to make this unique program possible. So thanks once again. Really excited to continue the conversation in many venues on and offline, and looking forward to beating this so we can all get back to in-person meetings before too long, and not spend the rest of our lives on Zoom as well. Thank you.
Happy anniversary. You're welcome.
Thank you, Rob. This panel has been great. I have to note that each one of our panelists is engaged with some activity in the community, whether it's county or city or the local schools, whether it is the hospitals, whether it is the classrooms and so on. And that takes quite a bit of not only time commitment, but quite a bit of courage, as Kim would testify to in educating people when there are conflicting commercial interests. It's good to know that the schools can be open, safely open, and not necessarily retrofitting entire HVAC system, but really through local cleaning. So let's hope that HDSI and of course UCSD in general can make that impact on the community. Thank you for the panel. And I'm going to hand it over to Associate Director Virginia Disa for the next session on introducing our new faculty.
Thank you very much. As you've heard, we have been very active hiring new top-rated faculty at HDSI. And in our next session, we are going to have a brief lightning talks by 6 of our recent hires. And we're very short on time. As you heard, the Chancellor will be following this session. So this session will be kept to time. And I don't want to take any more time. They're all going to introduce themselves. And we're going to start off with Dr. Yusi Wang.
All right. Okay. Thanks, Jeannie. So I'm Yusi Wang. I joined HDSI last summer, and it's really exciting to be in HDSI at this defining moments for data science. So I heard a lot about what is data science, and to me, an important aspect is to make sense of the world, to predict behavior through data. Okay. And throughout history, geometry has offered us a lot of important tools to do exactly so, like the Pythagorean theorem, like Euclid's elements. It provides us language to define and to quantify what we can see. Okay. And in the last 100 years or so, a new kind of geometry called topology has received significant attention and development. And by ignoring the detailed geometric information and instead focus on the coarser but essential connectivity information, topology also gives us ways to model what we don't necessarily easily see. Like here, the coffee mug and the donuts, they don't look the same, and turn out they have the same topology. And they both share this essential structure, the hole in the middle, the handle in common. Okay, so in general, topological language and method now give us ability to also model essential, potentially invisible structure behind not just the spaces, but also functions and the complex maps defined on them. Okay. On the other hand, in the current data era, we come across diverse and complex data routinely. But this data are not arbitrary. They have shape and structure, and such structures often essential to our understanding of both data themselves and also the processes that generate them. So to this end, it's natural that geometry and topology can help us to capture the structure of data. But we have to do so, we have to combine such classical objects. We have to extend it together with statistical analysis, with algorithmic treatment, with appropriate discretization and the computational consideration, with machine learning pipelines, in order to develop effective methodologies to analyzing complex data in different application domains. And this is exactly what this emerging field, TGDA, topological and geometric data analysis, aims to do, which I'm very excited about. Essentially, it aims to develop new ways to analyze complex data through this geometric and topological lens. So the use of geometric ideas in modern data science is more common, like manifold learning, diffusion geometry, or more recently, equivariant neural networks. So in the next couple of minutes, I want to give you some examples of how topological ideas has been used. Okay. All right, so here is a very simple but common data analysis pipeline. So suppose we're given a collection of objects. It can be a collection of images, or in this case, it's a collection of trees, where each tree actually model the morphology of a neuron cell. Okay. So typically what we do is that we map this object into some meaningful feature space and then carry out the data analysis task there. Okay. Now the choice of this feature space is important, and often we have to design different feature map to handle different type of data. And it turned out that by using something called a persistent homology, which is like a modern extension of a classical topological concept, we can actually have a generic framework to map different type of complex objects into a common type of a summary called persistent summary. Okay, and then you can then carry out downstream analysis, including specific dedicated neural network on top of persistent summary. Okay. So what is this persistent summary? Here's just a very simple example to give you an idea. Say I want to characterize this curve. It looks quite boring. And now imagine that if we now start to thicken this curve, and I thicken the curve and the track was what's the change in its topological feature, okay? Now, at this point, at the beginning, there was only one hole in the middle, but then at this point, we note that we now create a new hole in the domain, okay? And as I continue the thickening process, now this new hole created got filled, so it's destroyed, okay? And at this point, the original hole in the domain also got filled, got killed. Okay? So this process can be summarized by this simple diagram, which encodes the birth and the death of different multi-scale features through this evolution process, okay? And it turned out that in general, this idea can be applied to different type of data, be it images, just the points data, or directed and undirected networks. And it gives a very versatile framework to map different type of data into a multi-scale feature representation. Okay, it's already used in a range of applications. There's just some examples from my group. You can also use such topological summary to enhance other neural network pipelines. So here's where we use the persistent profile to characterize both local and global shape of the carbon nanotubes, and use that to enhance the graph neural networks to better predict the mechanical property of carbon nanotube composite just directly from atomic structure. All right, so this is an example where the summarization and categorization power of topology can help. Now, topology can also help to model and extract essential space underlying input data. Okay. Now, when we are given high dimension data, we tend to project to low dimensions and explore there. And often people tend to focus on the cluster structure behind data. But they're much richer structure of the space where data come from. And here's an example where instead I'm showing you a terrain metaphor of a high dimensional protein energy landscape. Okay, and here what we preserve where are the energy the valleys are created, and how do they merge with each other, and this information is precisely preserved in this terrain metaphor. Okay. You can also try to capture space behind a graph-like space behind data, and here's applied to RNA-seq data. We turn out that they naturally have a tree-like shape. Okay, the same idea also used for analyzing other type of data here. Let me just also mention that the topological structures can also be integrated with different learning frameworks to make those learning pipelines more structure aware. Okay, so here's just an example where we use the global structure to enhance UNet like neural networks to make them more aware of the global structure of the cell morphology inside in image segmentation. Okay. All right, so I hope this gives you some idea of how topological ideas can be used for analyzing complex data. I want to end my talk by saying that, of course, humankind has always interacted with the world around us through observations and data. Okay, so and through the course, mathematics, especially geometry, and computation, often by hand, has been the language of science since ancient time, like those tracking the motion of celestial bodies in the sky and so on. But in the current modern era of data, of course, now we face unprecedented availability of very complex data, diverse complex data, and also enormous computational power. So this requires to rethink how these classical objects, how can they evolve to make them more computational friendly? How can they be integrated with computational methods and algorithms so as to give us new ways to systematically understand and interpret data? Okay. And of course, this also requires diverse perspective and methodologies. And we heard a lot already, and the TGDA, topological and geometric data analysis, is just one such perspective by focusing on structure of data. And with that, thank you for attention.
Thank you very much. We have time for one question. If somebody has one, they can also be put in the chat or the Slido at any time. And Dr. Yusu Wang can answer them offline as well.
So a quick question, if I don't see anything on the chat though. It seems to me that the learning of manifolds, or putting data onto manifolds, is exploiting some kind of inherent information in the data sets. Are there information theoretic results there, like connection of information entropy to manifold learning?
I think that's an interesting question. I'm not sure. So there are a lot of work on how to retrieve this information when the input data is statistical. Namely, they are sampled in a certain model, but I'm not sure whether there's any information theoretical. Maybe there are work on if your intrinsic dimension is certain dimension, then, well, of course, there are work on that if the intrinsic dimension is D, then you need this much samples in order to recover the manifold, yes.
I see, okay. Thank you.
Thank you very much. We're now gonna move on to Dr. Yun Ma.
All right, I'm Ian Ma. It's very excited to see everyone here. Today, I want to talk about a computational aspect of sequential decision-making problem. In particular, I want to talk about how to leverage stochastic gradient Markov-Chain Monte Carlo strategy for that problem. Hope everyone can see my slides. So the problem about sequential decision-making is really two problems interacting with each other. We first need to sort of learn the environment, and then we need to use our learning about the environment to make decisions or control under this stochastic environment. And then after the decision is made, we collect more data from the learning in the next round. One crucial component in this process is that we not only need to learn to make accurate predictions, but also to quantify uncertainty of our learning. And we then use this learned uncertainty to facilitate informed decisions to be made. There are two ways to go about quantifying this uncertainty. One is the sort of frequentist approach, where we directly measure variations in the data. Another is the Bayesian approach, where we form probabilistic models and quantify the model uncertainties. So along the frequentist approach, many algorithms are proposed with understanding of their statistical and computational properties. The Bayesian approach, on the other hand, it is particularly flexible in incorporating knowledge about the system at various stages of the decision-making process. And there is a unifying framework called Thompson sampling or posterior sampling method that is widely used across industry. However, in complex problems, people often criticize that it doesn't scale well with the model and the data complexity. So let's tackle this problem. So what we want to achieve is that we want to, after we made a decision, and when we look back, we want to have as little regret as possible. And at the same time, we want to use a reasonable amount of computation to get there, to achieve to reach a conclusion. And by reasonable computation, what we really mean is that we are collecting more and more data as we make more and more decisions. But we don't want our computational infrastructure to take longer and longer to get to a decision.
So Ian, if you're sharing two different screens, you probably want to swap it. Otherwise, it's not a big deal. But you're sharing the speaker notes, but maybe the other screen is bigger.
Oh, okay. It's actually not a big deal.
Okay.
People can see my notes.
Okay, thank you.
Yeah. Thanks. Yeah, so to understand this problem, maybe let's start with the simplest scenario possible. That's the so-called bandits problem, where let's say we have a few options to choose from. And let's just like slot machines, where we pull the arm, we get a reward, right? And let's say the reward is distributed probabilistically according to a certain hidden distribution that we don't know about. Let's model it using a probability distribution that's parameterized by a parameter. And the Bayesian way of going about this is to maintain a posterior distribution for each of those options we can choose from. Let's say in round n, there are the posterior distributions according to each of those options, and they are in the space of parameters. So the Thompson sampling approach says that we can do the following. We can generate samples according to those posteriors, and then we can condition on those samples about the environment to compute the expected reward according to our model. And then we choose the action by maximizing over this expected reward. And this way will lead to the optimal regret. So the regret will be as small as possible, not just in the Bayesian sense, but also in the frequentist sense. Okay, so this is all well and good. But there are a few challenges, especially in terms of computation. First of all, it is oftentimes hard to generate exact samples according to those posterior distributions, especially when they're complicated. So we can think about using Markov chain Monte Carlo methods to generate approximate samples. Right? Along this line, a challenge is that we have a growing data set. So if we don't want to take longer and longer time to get there, maybe we can, instead of looking at the entire data set, we look at a subset of data every time within each iteration to use this stochastic gradient method. And what we need to achieve is that the algorithm must be getting more and more accurate, or the error must shrink as 1 over square root of n, where n is the number of rounds we play this game, so that we can still achieve this optimal regret. Okay, so maybe let's take a look at the stochastic gradient Markov chain Monte Carlo algorithm and see how we can do that. So in a typical stochastic gradient Markov chain Monte Carlo method, the error scales like the following. If in the nth round, let's say we take k iterations of this stochastic gradient Markov chain Monte Carlo method, then the error scales like the following. The error is upper bounded by the initial error times something that scales exponentially small with respect to the number of iterations we take. So that's good. What's challenging is that there is a bias term because of the stochastic gradient, which scales like square root of n, which grows over time, but it gets hit by a step size of the algorithm. So in order for error to shrink like 1 over square root of n, we need the step size to shrink like 1 over n. Right? This implies that within every iteration, we're making less and less progress. We're making less and less progress as the algorithm, as the number of rounds of game we play on. Right? Does that mean that we need to take more and more number of iterations along the way? So luckily not. We have something else up our sleeve. That's the so-called posterior concentration phenomena, which says that, let's say in round 10, the posterior looks somewhat like the following. In round 20, the posterior gets more concentrated. In round 30 and round 40, it gets more and more concentrated. And what's particularly nice about this is in round n+1, the posterior is actually not going to look so much different than the posterior in round n, which means that if we have generated an approximate sample in round n, it's going to be approximately distributed according to the posterior in round n+1, right? Which means in round n+1, we can just initialize our algorithm from the sample we obtained in the previous round, and then we don't have to make that much progress. And this generates the next theorem, which says that the Thompson sampling algorithm with stochastic gradient Markov chain Monte Carlo plus the warm initialization method we just mentioned, it only needs a constant number of iterations and a constant number of data samples per iteration to reach to an error that scales like 1 over square root of n. And that achieves the optimal regret that we're looking for. So in observance of time, I'll just acknowledge my collaborators and stop there.
Thank you very much. We have time for one or two questions. Again, you can use the Slido link or the chat. And if not, you can save them to the end. And if we have time, we can have questions at the end or ask them offline in the chat. Thank you. And our next speaker will be Dr. Mikio Aoi. And go ahead.
Okay. So just give me 1 second to get everything set up here. And let's see. Okay, how's that? Can you see this? Okay. So, I am a computational neuroscientist. I'm actually jointly appointed between HDSI and neurobiology. And so in general, I am interested in the brain. And I take the broad view that the brain is a computer that happens to be made out of meat. And I'd like to understand what the principles, the computing principles of this meat computer are. So we know that, for example, the computing units of the brain are neurons and that they communicate with each other with spikes in their memory potentials called action potentials. And more often than not, there's not just two or more, a couple of neurons communicating with each other, but many neurons communicating at the same time. Moreover, some of these neurons have direct lines of communication to other neurons. Some of them talk back, and there's the whole collection of these direct lines of communication constitute a network of communication with complex interactions. So what's important about this is that the network architecture, as well as the properties of the individual neurons, determine a specific computation that's implemented by this network. Unfortunately, we don't always know what those direct lines of communication are, or what the physiological properties of each of the individual neurons are. All we often have access to are just the conversations that the neurons are having, really just what they're saying, as if you're in a cacophony of a conversation inside of a big lecture hall. So the central question of my research is, what can we learn about the computation that's implemented by the brain if all we have access to are the conversations that the neurons are having? So most of what I do tries to attack this question using tools of dimensionality reduction. And I was going to talk about this today, but I decided that since there are quite a few people who do spatial statistics, I'm going to talk about something that's preliminary work because I thought it would just be more fun. Okay, so this project is actually one of those scenarios where we don't even have information about what the neurons are specifically communicating. Instead, all we have access to are what we might call the fumes of communication, where there are aggregate neurons, and we can take measurements of the collection of all of those neurons participating in a conversation. But oftentimes we might be able to define a strict organization of these different groups of neurons. So one example of this is wide field calcium imaging. So this is an example from my collaborator, Ben Scott at BU, where he has these freely behaving rats, and he developed a microscope that could be mounted directly to their heads without affecting their behavior. And he can take measurements of brain activity directly from the surface of the rat's brain. And so this is a little example of the size of the window. And sometimes when the rat's behaving or when it's exposed to different stimuli in an experiment, you can see little blips come on and off. But sometimes these blips aren't just blips. Sometimes they are waves that move across the cortical surface, or these blips come on and then move somewhere else and then turn off. And very little work has been done to characterize those waves or the things that move across the cortical surface. Most of the work's been done to characterize these the blips. So I'd like to be able to understand these kinds of phenomena. I'm calling them traveling waves. And so the goals of this project are, one, to have automated detection and classification of these kinds of moving events. There's tons of data here and potentially thousands of trials of a behavioral experiment that nobody can go through by hand. We'd like to be able to characterize the functional significance of these kinds of events, and we'd be able to use those events to generate hypotheses about learning, perception, and decision-making in these animals. So if we're going to talk about things moving across the cortical surface, we're talking about waves. And so if we're going to be able to characterize waves, we should ask ourselves, what is a wave? Well, if you ask a physicist what a wave is, then she might write down an equation and describe to you something that adheres to conservation laws or boundary conditions or initial conditions. This is an example of the wave equation. This is the advection diffusion equation. Navier-Stokes is another example. But oftentimes, not just oftentimes, I think with these kinds of data, there's no such conservation laws that we can rely on to accurately describe these data. And so the challenge is, how do we describe flows or waves across the cortical surface without committing to conservation laws? Well, we could try numerical differentiation across the cortical surface, but that's problematic also. The data are noisy, there are these irregular boundaries, and we also have visual obstructions that are unique to every animal, like these areas here, which are vasculature that covers the surface of the brain. So the idea that I've had is to use Gaussian processes to smoothly model the activity underlying all of these visual obstructions in the noise, and then use those Gaussian, the inferred Gaussian processes to learn a flow field around the corresponding activity. So I'll just sort of highlight how that kind of thing would work. So there are some really important properties of Gaussian processes that make this modeling framework possible. So if I have put a prior distribution over the fluorescence signal, that is the Gaussian process, and I have a likelihood for my measurements conditioned on that Gaussian process, that's also a normal distribution, then what I can get is a posterior distribution over the fluorescence, as well as posterior distributions over the gradient of the fluorescence. And in fact, I can get a posterior distribution of any order derivative that the covariance kernel allows. And that posterior distribution will always be normally distributed with a mean and covariance that you can just write down. So I can get a closed form expression for the distribution of any number of gradients, and I can use that to estimate a flow field. So what that analysis pipeline might look like is if I had data that looked like this, where I have a blob of activity that moves across the cortical surface and diffuses away. I can infer the underlying intensity. I can use spatiotemporal gradients to estimate the flow field. And if I can segment these data where the activity exists, then I can take each one of those segmented events and tag them each with a feature vector like the direction and speed of movement. So there are many challenges that still exist for this project. One is scalability. Gaussian process regression naively implemented scales as order n cubed, where n would be the number of x points, y points, and time points. So that gets really big, really fast. Also data management problems. There's just a ton of data to be able to handle for this kind of an analysis. And then identifying ways of segmenting and clustering the data to identify these individual events and tagging them with useful features. And then, of course, the data analysis itself, using those features and the segmented events to actually understand how these kinds of things contribute to learning, perception, and decision making. So this is a project with two different collaborators on two different projects. One is Ben Scott doing the wide field calcium imaging in these rats. That's the slide I showed you earlier. And then just recently, I submitted a grant proposal with Matthew Lovett-Barron, who's now in neurobiology, where he's doing whole brain imaging of neuromodulator dynamics in larval zebrafish. And there's lots of room for many other kinds of collaborators, including computational collaborators. And so I'm looking for students and collaborators. And so if you're interested in this kind of stuff, then we should get a socially distanced coffee or beer and talk about the brain. Thank you.
Thank you very much. We have time again for 1 or 2 questions, and excellent timing on the part of all of these speakers. There's a question in the chat or in the Slido saying, is accurate segmentation of moving features an important problem? This question's from Armin.
I'd say in this case it is. So one of the things that we know is that some of these features do seem to co-occur with specific stimuli that the rats were observing. And we'd like to be able to capture them all. So the only way to do so is either by hand or come up with an automated method that would do so by, that matches the by hand approach or better. So, our collaborators are certainly interested in those events, and we would need to get them automatically since there's so much data.
Thank you very much. Our next speaker is our very latest hire, Dr. David Danks.
while David is getting the screen, let me just say, welcome. This morning, David signed the dotted line. So he's really our latest, not even 24 hours. Thank you, David.
Thanks so much, Rajesh, and thank you, Ginny. As Rajesh mentioned, and Ginny, I'm not yet officially at UC San Diego, but will be joining this summer. I'm currently the Thurston Professor of Philosophy and Psychology at Carnegie Mellon, where it is at the moment snowing. So I very much wish I were in San Diego with all of you. So I wanted to talk about several different themes of research that I've been undertaking for the last little while. Interestingly, all of which have been foreshadowed by things that people have talked about earlier today. The first is in the area of causal discovery. So this is the general question of, given that we have a data set and we want to learn something like the causal structure. I mean, we know that anyone who's taken first year statistics knows that correlation is not causation. We saw many examples this morning in the keynote. But even here, for example, today, it is correlated. There's a correlation between the weather outside and whether people are wearing heavy jackets. But getting everyone here in Pittsburgh to take off their heavy jackets would unfortunately not make it any warmer. And so the problem of causal discovery is fundamentally the question of how do we go from data to the framework I prefer is the framework of causal graphical models, which is, for all the kinds of purposes that we're worried about, actually representationally equivalent to the framework that we saw in this morning's keynote, the potential outcomes framework. And so what I've done over a number of years is basically tried to develop novel algorithms for relatively complex kinds of data sets and data scenarios. So not just looking at the theory of causal discovery algorithms, but producing algorithms that actually are functional for the real world scientific problems that we're facing and where it is critical that we get causal information. So that includes cases of overlapping data sets, overlapping the variables where you don't have identification. So you can't create any unified single data set. So sort of the worst case scenario of what is sometimes referred to as federated learning. Cases of non-stationarity, where the causal structures change on us. The world is unfortunately not a stable place. And so causal structures that we learn in one moment can suddenly change on us with no notification. So how can we both protect ourselves against those kinds of changes and then rapidly respond when the world does change? Cases of unobserved variables, or most recently looking at the case of what's called undersampled time series. Now, you might wonder what that exactly means. It's actually pretty straightforward to explain given Mikio's talk. So he is focused on the fumes of communication in neurons, and he was focused on spatial aggregates. We're interested in temporal aggregates. So on the left, there you see an fMRI image, which samples the brain every 1 to 2 seconds. But the problem is we know that the brain communicates much faster than that. So how do we go from these very slow measurements to infer the causal structure at the time scale of the brain, where we don't even exactly know what that is? And so we've used these methods to gain more insight into the structure of neural pathways. We're also right now using it to better understand intraoperative hypotension events in surgeries, where people's blood pressures will suddenly crash and we don't have sufficiently rapid measurements to always be able to know exactly what is causing this. Now, a very different body of work that I've been doing is focused around issues in what we might think of as ethics, society, and data science. So most notably in recent years have been focusing on challenges arising from what is popularly referred to as algorithmic bias. So how do we improve our measures of these biases? How do we understand the different sources and causes of the biases in our algorithms? And perhaps most importantly, how do we have improved practices and regulatory policies to try to mitigate the very real harms and injustices that are perpetuated by biases and unfairness in the algorithms that are being deployed every single day? Now, that's not the only area that I've looked at in terms of ethics, society, and data science. I've also looked at how we can have autonomous systems that are more trustworthy. So Jeanette Wing earlier today mentioned trustworthy AI. And so the work here has been to develop basically a philosophically well-grounded theory of trustworthiness that can then be translated into operational criteria that we can actually hand to a software developer to try and have an autonomous system that is, in fact, more trustworthy than it might otherwise have been. as well as a range of other issues. So looking at the nature of explainable data science. Right now, there are many calls that we should be able to provide explanations for the judgments that are rendered by the algorithms we're building on the large quantities of data that are being collected. But there's I shouldn't say very little, there's insufficient work, I would argue, on what we actually want from an explanation. In many cases, explainable data science, explainable AI is thought to be something that a computer scientist or statistician can understand, rather than something that serves the needs and purposes of the end user or the person who's directly impacted by the decision. Related to all of this is how can we have practical guidance to have more ethical and responsible data science? I think there are a large number of principles being proposed, but how do we actually translate those into on-the-ground practices, whether in industry settings, in academic projects, or even just in our classrooms, so that our students, the next generation, are learning the best practices from the very beginning. And there have been a range of other projects that I've been doing in this space. I won't go into all of them. I'll just note this last one, since it came up in regards to the COVID panel, looking at issues around disinformation, including how it is propagated, the role of recommendation systems in the spread of disinformation, and how we can educate people to be better protected against it. So how we can improve what is sometimes referred to as the social cybersecurity, not just protecting the ones and zeros, but protecting the humans in the information ecosystem. Now, one of the things I'm really excited to be able to pursue coming to UCSD is actually an integration of these two different lines of research that up until now I've kept relatively separate. But that is trying to build systems that can actually do automated discovery of philosophically defensible biases. So not just looking at bias as a kind of surface feature of our data in the sense of this group has a different false positive rate than that group, but rather trying to uncover the underlying unobserved causes of those statistical disparities. What are the underlying biases, and how do we morally and politically evaluate the biases generating the data that we're seeing? So that project has a number of different components. And they're components that I think I'll be ideally positioned to pursue at UCSD. And certainly everything I've heard today has confirmed that. And I just want to end by saying one of the key parts of this program is to actually develop practical tools for the next generation of data scientists. So not just proving theorems, though that's important, not just developing algorithms, though that's important, but translating those into tools and practices so that we can actually produce data science, data analytics, AI, machine learning systems that serve the interests and values of the many rather than just the few. So thanks so much.
Thank you. We have time for a couple of questions. Again, you can put them in the chat or in the Slido.
Or perhaps everyone is completely convinced we need causation, we need ethics, we need to put them together. Sounds like a great plan to me.
Okay, again, we can have time. Everybody's talking to time, so we'll probably have time at the end for questions for anybody. So if you think of something. And then next speaker is going to be Dr. Babak Salimi, and he's already got slides up.
Yeah, perfect timing to talk about causal data science. Hi, everyone. My name is Babak Salimi. Today, I'd like to give you an overview of the topics that we research on in my research group, causal data science, and briefly discuss one of my most recent work in the context of inferring causality from a complex relational data. So the ultimate goal in data science is to extract value out of data and turn it into actionable insights that can eventually improve people's life. In this space, my research is motivated to address the following key questions in data science. How can we ensure the conclusion that we make out of the data science pipeline are fair, valid, accurate, and reliable? How can we build transparent algorithms so that our conclusion and decisions becomes indisputable and the customer would trust our systems? And how we can remove bias from data and protect data from bias during its life cycle. In my research group, we look into the entire data science pipeline to address issues related to bias and discrimination at different stages. Fundamentally, we have raw data, which goes through this pre-processing, a step to become ready for analysis. We process data using either analytical queries, machine learning, or data mining algorithms, and then we use the result for decision-making. In most situations, the problem is with the existing bias in data, and our work in the context of algorithmic fairness addressed this issue by bringing together techniques from graphical models and databases to kind of clean data for the purpose of data analysis and machine learning. Even if the input to the data science pipeline is perfectly unbiased data, each and every step during the data preparation, for instance, during data cleaning, integration, filtering, they can actually introduce bias out of the blue or exacerbate the existing bias. Our ongoing work in the context of what I call responsible data management brings together techniques from graphical models again, data provenance, query optimization, to develop efficient systems for protecting data from bias at different stage of its life cycle. And then I believe generating different forms of explanations in data analysis is crucial for trustworthy data analysis, avoiding bias and false conclusions, and for understanding data. I have ongoing projects that look into generating explanation for black box machine learning algorithms using counterfactual reasoning. And finally, my research is grounded in causal inference, since I believe causal inference can serve as foundation for capturing and discovering different forms of biases and discrimination, avoiding false conclusions, and for generating explanations. But I also contribute to the causal inference itself by providing the theoretical foundation for learning causality from complex relational data, which I'm going to briefly talk about it next. Again, I don't need to advertise causal inference after the great keynote and panel discussion that we have today and after David's talk. But causal inference, as we know, is at the heart of decision-making in natural and social sciences. It's crucial in several disciplines such as clinical research, public policy, economics, business, and as we discussed, for reasoning about bias and discrimination. Despite huge progress in causal modeling and analysis in the past 2 decades, the existing theories of causation, they rely on 2 restrictive assumptions. First, the domain of a study should consist of a bunch of homogeneous or similar entities, for instance, bunch of customers, bunch of patients, bunch of students, and therefore the data is naturally sitting on a single flat table that you may store in a spreadsheet like this. The second assumption, which is more fundamental, is that there's this underlying assumption that there is no interference between the units of analysis, which intuitively mean statisticians assume units of analysis could not interact with each other. This is the SUTFA assumption on Emmanuel keynote talks that we saw earlier. However, in most practical situations, we are dealing with complex relational data, and relational domains consist of heterogeneous entities that in which the underlying causal structure exhibit complex phenomena such as network dependence, interference, contingent, and homophily. For instance, suppose you're interested to find out whether authors' institutional prestige has any sort of effect on their paper acceptance rate, which has to do with fairness and bias as well. This is a relational domain consisting of heterogeneous entities such as institutions, person, authors, and submissions, and in which units are connected through different social and organizational networks. So all of the underlying assumptions in classic causal inference, they are actually invalid in this case. So surprisingly, we don't even have a comprehensive theory for answering such questions. This motivated us to introduce CAR, a theoretical foundation for causal inference from complex relational data. At the core of our framework is a logic-based language, using which user can declaratively express what they already know about the relational domain and what they want to know. And it is the underlying inference mechanism that computes the answer to their queries. The declarative nature of our system makes causal inference accessible to users with no or little background in causal inference and statistics. Just to give you a sense of the internals of our system, I included this slide. It's pretty dense, but what it says is basically it reflects the system's inference pipeline of CAR. Using our system, user express their background knowledge, And they're causal according using a set of logic-like rules called relational causal rules. This is just an example of relational causal rule here. Then the underlying inference engine compile these rules into what we call grounded causal graph. And then the system uses these graphs to eventually denormalize or flatten relational data using embedding and schema traversal techniques to make it ready for sound causal analysis. Let me share with you a cool experiment here. So we applied Carl to open review data, which is a relational data consists of a collection of submissions and their reviews to several machine learning and AI conferences to find out whether authors' institutional prestige really influences the reviewer's decision. We found out that in both single blind and double blind venues, there is a positive correlation between prestige and review scores as expected. However, once we used CAL and performed causal analysis, we found that while in single blind conferences, the reviewers might be influenced by prestige of authors, in double blind conferences, that is not the case. So this kind of suggests that double blinding can indeed reduce reviewers' bias. Okay, let me conclude my talk here by saying that if you're a social or healthcare scientist or a business decision maker with a causal inference problem from a large relational data, with a complex schema, which looks something like this. And if you eliminate the hassle of working with relational data by just joining these base relations together to obtain a single table that you can store in a spreadsheet and then use your favorite statistical software, Python or R to analyze your data, then I should warn you that your analysis could be potentially biased. And I would be happy to have a virtual coffee with you and discuss whether CAL can help you to get rid of the potential bias. So feel free to drop me an email. Thank you all for listening.
Thank you. Thank you very much. Do we have any questions for Babak? There's a question in the chat. Can your approach support physics-based or behavior-based data to augment causality understanding?
Are these structured data or unstructured data?
Structured.
Yeah, it is independent of the underlying domain, so we can basically work with any sort of structured data.
Are there any?
So I have a question that actually spans both David and Babak. I somehow see the two poles to what David was presenting, but it seems to me we have some kind of a logical quandary here when it comes to bias. For a very long time, the understanding was that the humans were the cause of bias, and we sort of live with that metaphor. You know, this is what the computer tells me, for example, was the classic refrain when somebody was asked, why am I not getting a seat or whatever preference. And David, you refer to the idea that bias is somehow not a surface characteristic of data, but something more inherent. And I was just trying to peel that, what that inherent thing is. If I peel that thing, the Babak will tell me probably that this is the longitudinal data. And I hope the philosophy tells us there's a human sitting inside there. Is that the case? I mean, are we trying to create models of human in trying to debias data?
I'll go ahead and jump in. I mean, I think what I'm interested in doing is understanding from data the possible structures that produce the observed data that we actually see, perhaps in response to policy changes, and then being able to understand which of those represent either historic or systemic or in the moment injustices. Not all biases ought to be corrected. So any system that gives equal numbers of diagnoses of prostate cancer to men and women is not a very good system. We know that they're biases, but we don't think that they're problematic biases in any moral sense because we understand the biomedical underlying reasons. I think the challenge is that we have a lot of biases in our data in the sense of skews, and we don't know which of them are problematic, which are simply the result of normal human behavior, which need to be corrected. And so I think we need better representational languages, and causal models are a key part of that.
So some kind of a value system, like Kantian value system, needs to be attached to bias assessment before we, of course, as you know, in those days it was goodness, but now it is fairness. And so the discussion remains the same.
Let me also add that,
yeah.
Go ahead, Register. Sorry.
Go ahead, Babak.
Yeah, I was also wanted to add that it very much depends on which type of bias we are dealing with here. So bias could be historical bias. It could be the bias that we actually introduced during the data collection. It could be bias that happens as a result of, I don't know, a data imputation algorithm that actually skew the underlying distribution. It could be a butterfly bias or collider bias that may be introduced during the feature selection when we select features for training a machine learning algorithm. And it is very important that dealing with these different types of biases require different sorts of tools, and all of them are kind of confused in the context of algorithmic fairness literature. Yeah.
And I would just very briefly say, Rajesh, you're absolutely right. There are a lot of interesting value questions that need to be asked. And I think that's what Emmanuel was getting at this morning when he wanted to distinguish statistical from policy, is the value questions have to be asked in addition to. I just think we're all already doing that anyway when we do data science. We just aren't necessarily recognizing the value choices we're making.
Thank you. We could take this on, but let's in the interest of time, let's get Lily to come on. Thank you.
Yeah, thank you. Our final speaker is Dr. Lily Wang.
Hi, can you see my slides?
Yeah.
Okay, great. Yeah, hi everyone. I'm Lily Wen. I will be joining HDSI in July, and I'm happy to see you all here and share with you my research about quantifying robustness of neural networks. So we know that deep neural networks are everywhere. So you can see it in computer vision for image classification tasks, and also in autonomous driving for pedestrian detection and so on, and also in the natural language processing and speech for this machine learning translation, text classification, as well as speech recognition. It's actually also very popular outside the traditional artificial intelligence area. So you can see neural networks in medicine, biology, security defense, finance, robotics, and also, of course, this very famous DeepRL agent to play Go. Despite the success of neural networks, however, they are actually not as safe and trustworthy yet. As an example, they are vulnerable to adversarial attacks. So what is an adversarial attack? So suppose you use your neural network during the test time, and it's perfect that it can classify this panda image correctly. However, at the testing phase, it's possible to have an attacker trying to craft this adversarial perturbation on your original test data. And then now your neural network does not recognize this image anymore. So this perturbed image is called adversarial image because for our human eyes, we still think it is a panda, but now the neural network doesn't recognize it. Unfortunately, there are more adversarial attacks. So imagine in your car, if your camera is driven by like a machine learning model and it doesn't recognize a stop sign, that will be very miserable. And also it has been shown possible that there could be these 3D adversarial examples which raise a very serious security concern. And of course, there are like more and more adversarial attacks in various machine learning models, for example, in image processing, image captioning, and also this in automated speech recognition. Perhaps more surprisingly, the deep neural networks also vulnerable to the non-adversarial random perturbations. So in this case, the neural network, now we don't have the attacker, but simply random noises. And now the neural network cannot recognize this perturbed image as well. So the topic I'm going to focus on today in this talk is about the robustness in AI/ML systems, particularly for the neural networks. We know that deep neural networks are already powerful, but I believe we need more than just superior performance. And what I mean is that we want to be able to verify and also assess the systems if the system can produce consistent answers upon perturbations. So speaking of robustness, there are actually many types of perturbation that you can consider. So the adversarial perturbations that I gave an example before, and also this non-adversarial perturbation, including random noises, natural variations, and also it's possible to have model parameter shifts, as well as the distributional shift between your test set and training set. And it's also possible to have the data poisoning, which is kind of like the attacks in the training phase. So today I'm going to introduce 3 types of perturbation and how we can verify upon this perturbation for the neural networks. So I'll be focusing on the adversarial perturbation as the first part, and also the random noises, and also lastly, the semantic perturbations. So this is like a cartoon graph of how we define robustness of neural networks. So X0 is our original test image. And here I plot out the adversarial examples because they are not classified as ostrich anymore. And we can plot out the amount of perturbation of the attack. So ideally, an attacker wanted to find out what is the smallest perturbation like that they can craft in order to fool your neural network. On the other hand, when we trying to look into this problem, we are trying to find out a certified robustness region. So instead of finding an adversarial examples, we wanted to quantify a safety region in green circle, so that within this region, there's no misclassification can ever happen, no matter how your perturbation is. And we usually quantify the region by the radius. So what are the challenges? So ideally, we wanted to find what is the maximum uncertified radius we could have. But unfortunately, it has been proved to be an NP-complete problem. So as an example, it will take 3 hours to just calculate the radius for one input on a tiny network, which only has 300 neurons. But fortunately, our work and also from several other groups, we show that it's possible to find a non-trivial lower bound for this certified radius. So we can find a smaller radius, non-trivial smaller radius, but much faster. So for example, now we can boil down to several minutes and seconds for state-of-the-art deep neural networks or relatively large neural networks. So for the first type of adversarial perturbation, we proposed Clever score in 2018, which is the first practical algorithm to evaluate the robustness of neural networks. And we also proposed a series of linear bounding framework, which can apply to generativation functions, many different building blocks, and also the recurrent neural networks. For the random noises, we proposed the algorithm called Proven, where we relax the worst case guarantee to the probabilistic guarantee. And for the final one, the semantified neural network, we are able to certify the robustness to the semantic perturbations like rotations, lightning, and so on. So for the first part, the Clever score, the idea is that we are able to approximate the smoothness of the function, and by drawing the samples at the input space and evaluate the gradient. And so there we can give out the robustness score to evaluate the robustness of neural network. And for the second part of algorithms, the FastLink-like algorithm, the key idea is that you can classify the neurons based on the status of the activation. And so there, the key idea is that we can bound a nonlinear neural network by 2 linear functions, and therefore to verify the robustness. So as a little showcase of the experimental results on standard image benchmark, you can see that for smaller data set, we tend to have a larger robustness, while you scale to the ImageNet, which is the most realistic image data set, then the robustness score is actually pretty low, meaning that it's very vulnerable to adversarial attacks. And due to the time constraint, I'm not going to talk about this experimental results, but essentially you can try to, if you're interested, you can check out the papers that we are able to provide polynomial time algorithm to efficiently calculate what is the robustness radius. And for the second type of random noise, the perturbation on the random noise, the idea of this work is that we can actually bound the probability of no misclassification mathematically by the CDF of the linear transformation of random variables. So the idea here is that we can build on top of the existing worst case tools that I talked about earlier. And by using a concentration inequality, we are able to find out what is the probability of the margin greater than 0. And for the last part, it's about a semantic perturbation. And the key idea is that it's possible to show that this semantic operation can be expressed as the neural network layers. And therefore, we can also build on top of existing worst case perturbation verifiers. Okay, so today I talk about these 3 different types of perturbation and how we are handling this with various approach. And I wanted to spend 2 more minutes to talk about what's next. So in my research lab, I plan to be focusing on how can we build safe and trustworthy deep neural networks. So here are 5 different topics that I'm interested in. So the first one is about robust training. So at the end of the day, people care about how you can make neural network more robust. And so it's possible to include the verification bounds that I talked about earlier into the training phase. And therefore, you can make your neural network more verifiable or more robust. And also, we also want to have a more scalable verification. And recently, there's this randomized smoothing techniques trying to make your verification black box and more scalable. And also, it's possible to investigate the robustness beyond inference time. For example, the data point sending attack that would happen in the training phase. Also, it's possible that your model parameters might be vulnerable to perturbation. So this type of attack is called error injection, and how to develop the robustness certificate and training, that would be an interesting topics. Finally, I'm also interested in the application beyond classification. So for example, if you have a deep RL agent that's driven by the deep neural networks, and you can see that it's possible to attack the deep RL agent. So this is more complicated because now you have this AI in a loop instead of the simple classification problem. So essentially, I care about the scalability and efficiency of the algorithm as well as the provable guarantees. So moving forward, I think we also care about beyond robustness. So I think I'm very happy to see that people now care about robustness beyond accuracy. And I think that we also care about fairness, interpretability, and privacy, even security in different settings. So I'll be interested to apply these tools into the applications, including robotics, healthcare, and transportation. So yeah, so this is the end of my talk. I'm happy to take any questions.
Thank you. At this point, we can also open it up for any questions for Lily, but also any questions for any of the speakers. And I already have one queued up, so I will give first priority to any for Lily, and then let's see. So there's a question from Armin for David Danks. It says, ethical bias appears to be a subjective quantity determined by values, but you would like to detect it in data. Is there an objective way of measuring ethical bias so that it can be discovered in data?
So yes, with assumptions. So this is one of the ways in which I think this project draws inspiration from some of the work on causal discovery, is the acknowledgement that you can't just go from descriptions of data to a causal structure without having some kind of domain general assumptions. So there are assumptions that one needs to make about how particular mechanisms manifest in data and about certain kinds of values. It's very tempting when we start thinking about values in data science, values in AI, to jump to what we philosophers would refer to as value pluralism, the idea that my values are probably somewhat different from Ginny's or somewhat different from Lily's. But I think we need to be careful because those can frequently mask enormous amounts of agreement. The example I often use with my students is, I don't need to know exactly what your value system is to know that it would be unethical for me to walk up to someone on the street and push them over and take their wallet. Essentially, every value system of a normal citizen is going to say that that's not an ethical thing to do, except in extreme circumstances. So you're absolutely right that we need to bring values to bear, but I would argue we're already doing that in data science. We're already prioritizing accuracy over access in certain kinds of cases, or minimizing cost in other applications. We call it a loss function and we optimize it. So I think we're already doing it. We just need to do it in a more intentional and participatory way, actually engaging with the communities that our decisions are impacting. So great question, but I think there are things we can do.
Are there any other questions for any of the speakers?
I have a non-technical question. So if I look at the 6 faculty members who just gave the talk, and if HDSI did not exist, I don't know if more than any 2 of you, or even any 2 of you, would be in the same department. So I know some of you are already here. Mikio, you're here. Babak, you're here. Ian, and some of you are not. How do you feel about joining a unit that is so distinct? And I know we have a few minutes. I think Chancellor comes on next. So see if you have any sentiments on that.
I'll just quickly say, I'm over the moon with excitement. I'm at a university that prides itself on being interdisciplinary at Carnegie Mellon. And I feel like I'm coming to an even more interdisciplinary place. The idea that, I didn't know anything about Mikio's work, and the idea that he's looking at a very similar problem, but in the spatial domain rather than the temporal one in regards to neural firing patterns and inferring communication networks. I'm just so excited. I want to move now, and not just because it's snowing. So I think it's wonderful.
Yeah, the other day I was, someone. Oh yeah, the other day I was talking to my, it's Babak. But I'll just finish. The other day I was talking to my wife saying, oh yeah, let's after the pandemic is over, let's just find a time, find a beer, sit down with a philosopher or with a neuroscientist. Let's just chat. So, well, that's more exciting than, everyone being computer scientist or statistician, right?
So about me, my background is in databases and in causal inference, and I do responsible data science. And then I think it's incredible. I'm in a situation in which I have access to this incredible database group with Arun Kumar, Vitor Viano, Yanis, lots of famous figures in databases. I'm looking forward to talk with David. I'm very excited, and we have a lot of research interest in common. I already started working with Bert. With him, both of us are interested in algorithmic fairness. We also started talking, brainstorming some project with Molly. So yeah, it's an incredible place. I wouldn't have this opportunity anywhere else for sure.
I'll say, when I was applying to grad school, I entered an interdisciplinary program, and I had people specifically warning me against interdisciplinary programs and interdisciplinary work because they said I'd never get a job. And I think I have just found a lot of fun doing the work that I do. I know I could be doing something else, but there's nothing more fun than, as Jan said, to be able to talk to a philosopher and a computer scientist and a neuroscientist all at the same table. So that's what's rewarding to me about this kind of work.
Let me just add one sentence. I mean, I always work with some people from mathematics, from applied domains, but I feel, I mean, you can always find people who has the expertise that he needs. But I think with this platform, what happens is that you find not only people with that expertise, also people with the open-mindedness that is willing, that is very interested in work together. So I think that makes a big difference.
Wow. The experiment has already started. You will be in the same building. Everything points to that by the end of this summer quarter, maybe even a bit earlier. So with that, I'll leave it to Dimitris and Jenny for the next session.
Well, thank you. Thank you all for this very wonderful barrage of little talks. I'm delighted to introduce Chancellor Pradeep Khosla. Chancellor Khosla has done wonders for UCSD, not the least of which was UCSD's pandemic response. As a matter of fact, almost a year ago today, it was Monday, March 2nd, a year ago, was the last live event that I can even remember. But at some point we had many people. At some point we saw the leadership, and I guess Chancellor Khosla had gathered an emergency meeting involving the AVC, and everybody, and they decided on the spot that they should move all classes online, and that was weeks before any state recommendation, let alone federal recommendation. So and then it has continued. I mean, all the UCSD has been ahead of the COVID since. You have the return to learn, we have all the testing, even the vending machines, and now we have the vaccines. And some of us actually met yesterday at the vaccine administration. We're very grateful. Anyway, and on top of everything, Chancellor Khosla has been a staunch supporter of HDSI since its launch, and I'm very happy to welcome him to say a few words on our 3rd anniversary.
Thank you, Dimitris, and thank you for inviting me. And let me just say a big welcome to everybody. I just scanned the 4 screens with postage size faces, and some of you I know, many I don't, and that just goes on to tell you the vibrancy and the vibrant nature of HDSI and how it has brought so many new people on board, not just within the HDSI umbrella, but also at UC San Diego. So the last 3 years that HDSI has been in play, there has been very significant growth, not just in HDSI, but also at UC San Diego. And I only wish that we were doing this in person so you could see the tremendous growth of this campus in graduate housing, undergraduate housing, new programs. I can just go down the list. And I think HDSI is just one very important component of the growth. So if you think about a vibrant university, especially one as vibrant and as prestigious and as impactful as UC San Diego, it would have been a travesty not to have data sciences as a discipline on this great campus and this great university, because data sciences in this day and age is one of the only things that basically connects all sorts of dots together. So we talk about inter and multidisciplinary research. Data science, basically, if you do that research, you are at the intersection of multiple disciplines automatically. And I think the best way to think about that is UCSD is the best way for that to happen. This is a place where, if I may remind people, cognitive science as a department got birth long before it was fashionable. This is the place where neural networks were born long before they were fashionable. So this place, you can imagine now, would be just the natural place for data sciences also to have a very strong presence. So as you know, HDSI already celebrated its first graduating class in 2020. Unfortunately, it was remote, but nonetheless, I'm so glad that the class graduated, and I can tell you these students are going to be the 50 students who graduated are going to make a tremendous impact. And this spring, we're talking about 250 students in 3 years. This program is like the 8th most sought after program on this campus. And I think it's 8th only because we have to limit the number of students. As we expand HDSI, as HDSI's reputation expands, I can tell you this is going to be the go-to place for a whole lot of problem solving on this campus, but also in this country and in the world. Let me also say a big thank you to our faculty members. I know you guys, even if you come from multidisciplinary places, your faculty, your advisors, your peers, your senior faculty, wherever that place is, are typically more conservative than not. And the advice always is that, oh, don't go to a multidisciplinary place, try to fix it, be in your discipline, try to be in one department. I think you will find out that UC San Diego is very different. Here, if you are in 2 departments, the tenure condition is an or condition. So this was one of the innovations that I always wanted to make, even at a place like Carnegie Mellon, but I could not. But once I got here as chancellor, I knew I could make it here. So it's an or condition. So if you're a young faculty member or a senior professor, that the condition is an or condition. So that way the 2 departments have to compete to keep you happy and to keep you engaged. And it's not your problem to keep the departments engaged, which is a very different paradigm if you just think about this. And HDSI, I think many appointments here are going to be joint. Some will be not, but many will be joint, because this is the place that I want to use, or I want it to be a role model for what a good multidisciplinary research center should look like. Let me also say a big thank you to Taner. Taner, I know we've had many conversations since the day we talked about the big grant you wanted to give to build this place to today. Thank you for your support. I think your confidence and your ability to believe in HDSI is very significant. It actually gives us not just moral support, it also empowers us significantly, and especially Rajesh. Let me say thank you to Rajesh for your leadership. You've been truly amazing. And partly you've been amazing because you are amazing, and partly you've been amazing because people around you are amazing. So let me just say thank you to the people around you, like Ginny and Dimitris and others who are in your partnership. So you guys are truly amazing. But most amazing of all, I have to tell you, are the faculty members. I've been watching the hiring very carefully. Not that I listen to what I say, but I can at least watch what you do. And I've been extremely impressed with the people you brought in, and I think they're going to make this place truly spectacular. So let me just say, I apologize for being here at the end of the day, but this has been a crazy day. If you've been watching, there's a vaccine fiasco going outside that we have to manage, where we have people lined up who are ready to be vaccinated, but there are no vaccines on the other side. So that's what I've been managing all this. I really apologize for being here at the end of the day. Thank you very much. And let me hand this back to you, Dimitris.
Thank you, Chancellor Kosler. So now we're moving on to the next part of the program. I would like to introduce Aaron Frankel. Aaron is a lecturer with HDSI, but he's also responsible and chairing the undergraduate program. And a big part of the undergraduate program is the capstone projects. So Aaron will tell you all about that. So Aaron.
Great, thanks, Dimitris. And can people see my slides?
Yes.
Okay, perfect. Great. So I wanted to, it's my pleasure to be able to talk about the data science undergraduate program. And so just as a, let you know my plan, right? So I this being an anniversary event, I want to, kind of highlight some of the past, 3 years with respect to the program, and talk more about this sort of explosive growth that the major has seen, that the chancellor mentioned. And then actually I want to talk a little bit about the nuts and bolts of the program and show you, what we're teaching, what our students are learning. And then lastly, as as is in the name, I want to, go through and show off, our capstone sequence and these projects that our students are working on. Okay, so in the last 3 years, data science has, was incubated by computer science, math, and cognitive science with help from their courses and their faculty. And in the past year, 3 years, data science has grown, from that incubation, and we now have quite a few more courses and a lot more faculty and a lot more students, but we still retain the connections to these 3 departments and a lot more of the university now. So we've gone from just 131 majors in 2017 taking these classes, DSC classes, to 759 majors today, and then another 250 or so minors. So we're around 1,000 students in our community, 3 courses to more than 20, only 2 instructors to more than 20. And then I can't stress enough that one major cornerstone of this of the data science program through this entire time is sort of a focus on hands-on projects, starting from sort of bootstrapped enthusiasm from the Data Science Student Society to now we have sort of a large infrastructure in place, with staff and faculty giving students opportunities with our industry partners through our scholarship fund, the capstone sequence, as well as sort of more ad hoc approaches. So now a quick trip down memory lane. So of course, in 2017, we were, before I was here, we were really only 2 DSC courses, Intro to Data, Principles of Data Science, and then a workshop, and these were taught by 2 of our lecturers, Marina Langlois and Janine Tiefenbrook, who I should say are still huge contributors to our program in our lower division sequence. And then of course, a hat tip to Brad Wojtek's COGS 9, which is, while not being in the DSC course code and in the DSC program, it was and is a requirement for all of our students to take. After, in 2018, the data science major became, an official undergraduate program. The foundational lower division courses were really set. The program hired their first 100% faculty to teach for the program. Me being one of those hires, Justin Eldridge being the other, as well as our first ladder rank faculty hires with Gal Mishna, Yan Ma, and then Jingbo Chang. During this time, the student population was exploding. Popularity in data science was huge, and we had to find ourselves tapping the brakes and capping the major so that we don't grow out of our britches. At this period, and during this time, this is when we moved to our temporary spot in the Supercomputer Center, and we were still, while we had foundational courses set, we were still borrowing our advanced upper division courses from other departments. Last year, this photo, last year we had our first graduating class of 50. This photo was actually taken just barely over a year ago, on one of the last weeks on campus. And this was our 50 or so graduates outside the CSE building, the Capstone Lab. I like to call them our trailblazers. Sometimes I would call them our guinea pigs. They were a great group of students doing great things now with wonderful positive attitudes. And now, of course, in present, we continue to grow. We're hiring like crazy, as you've seen all day. You know, everybody is enthusiastic. You know, our new faculty are so enthusiastic about creating, you know, new advanced electives, working with our students, mentoring our students, and building future programs. A lot of these joint programs, or of course our graduate program, as well as, you know, a potential new minor. Okay, so let's take a look briefly at the actual capstone, our data science program, the major, and how it compares to other programs, you know, or just data science being taught around the country and the world. So everybody has likely seen the data science Venn diagram of, you know, this, you know, data science being made up of computer science, math and stats, and domain expertise, and data scientists kind of lying in the intersection. So this is these coordinates are, you know, sort of dual to that notion, where you get to choose, when you get to choose a data science curriculum or build one, you have to choose how many units, you know, how much time is spent learning each area, right? And a lot of programs out there, you know, a lot of universities don't have dedicated data science majors. Very few actually have them still. But a lot of programs still at least try to expose their students to data science. And perhaps just including domain-specific courses into an existing program, or doing something like taking, you know, in a statistics major, you know, adding some foundational CS courses, as well as, you know, data science, you know, flavored courses to add an emphasis to an existing program. What we do is really make our students learn everything. And it's ambitious, but we have them learn a large number of fundamentals, both from computer science and statistics. And we make sure that they get a lot of practical exposure, both to the domains that generate the data that they study, and specifically from experts in those fields, and not just, you know, experts in data science foundations, and really try to make our, you know, give our students the tools and the knowledge to apply these foundational skills that they learn. So generally the main branches of the major fall into sort of managing data, machine learning and statistics. And so machine learning kind of falls a little bit between math and stats and computer science. And then they take quite a few you know, computer science and data systems types classes as well. But while they're learning, you know, these foundational courses, we have made sure that students have these sort of frequent touch points to ground the theoretical learning in practical contexts. And these are these courses in yellow, which, you know, at every few quarters, students have to pause and apply and, you know, see the theory that they're learning in action. And then, of course, through their whole through the program, we give them some flexibility as well in exploring a domain that they're interested in, and that is sort of relevant to both their interests as well as data science in general. So this focus on doing these touch point courses that give the students the opportunity to apply what they're learning. These typically, you know, let students pause and you know, focus on sort of holistic, I like to say, holistic approaches to problems, for which the theory that they've learned would prove useful. And so they learned, for example, in COGS 9, how to ask questions. You know, the basics of how you might answer a question with data in a hands-on way. In DSC 80, their sophomore year, they learn to actually put a project together and deal with messy details and learn how important those messy details are. And then lastly, in the capstone, they really get to put all of their learning together into a 2-quarter-long project. And at the end of the program, what we really hope for is that students will graduate with a portfolio of projects that vary in style and purpose. And so what you see here on the slide actually is a portfolio that one of, an alumnus of the program who graduated last year put together, Enrique Sanchez. These projects, they came together from a combination of classes, mentored research, self-driven investigations, and the capstone. And so even these 4 came from both research positions that Enrique had, classes, working with certain faculty members on projects, in his own time. And the student portfolio integrates sort of student learnings across courses and in the program, and it lets them show off what they can be. Okay, so now, of course, we talk about portfolios and what's the main, what we hope is sort of the shining example or the capstone of their portfolio would be the capstone sequence. And so I wanted to take you through, what our seniors are doing right now. So what do we, what do we want from the capstone sequence within our major? So we want, for one, every student in the major to complete a capstone sequence, which is an unusual thing. Most programs in the areas that, especially touching computer science and math, advanced or honor students might do a capstone or an honors project, but rarely is it every student. But the sort of practical application, the practical grounding of the field of data science is so important that we found that it's of utmost importance that every student get this experience. And this experience should be a 2-quarter, 20-week project under close guidance of a mentor. They should learn what it's like to work on a team of data scientists on a problem, and start with the problem and approach this problem and figure out how, what the problem needs, from the perspective of trying to solve it, as opposed to, I have a method and I want to apply it. And of course, the capstone will add, a rigorous, nice, large structured project to student portfolios that they can be proud of. So what are some of the challenges of the data science capstone? Of course, the scale of the data science capstone and having 250 students, is difficult. But there are also some peculiarities of offering a capstone in data science. One is that data science is so broad, it can really span almost anything you can think of. And finding sort of enough mentors that can reasonably advise a good, broad student interests is difficult. And then, of course, actually consistently evaluating that work and across such varied areas is also tricky. Data science students also have a flipped background from what you would expect in most majors. And of course, this is just what the life of a data scientist. But students, they come in, right, without any domain knowledge, and they have to quickly get up to speed on this domain. But on the other hand, at least they do have a robust methodological toolkit or data science toolkit that in a traditional capstone in a subject area, right, students may not have. So how we approach this is that mentors sponsor sort of a domain of inquiry that they're comfortable with. And that domain supports multiple projects. And so you have a number of smaller data science teams working on related areas, and they can kind of work with each other and bounce ideas or problems off of each other, and kind of sort of work loosely in parallel in the same area, making progress that way. And during this time, they work with their domain mentors on these teams to get a quick introduction to their domain, build up a project proposal, because learning to ask the right questions in data science is a very important skill. And then, of course, they try to execute on their project, that they've proposed, and then collect their results in various, various formats, right? They build websites, they give presentations, they write up a sort of a report or a white paper, and they have their code, public and well presented. In parallel with this, we're also making sure that they develop a data science project that conforms to best practices in data science. So this would be creating a reproducible project, right? One that is deployable in multiple environments, is documented and versioned properly. So what do some of these domains of inquiry look like that multiple teams sign up for? So here we actually have domains, most of the domains from the last 2 years. And you see a wide variety represented here, from sort of technical business problems, from our industry partners in Viasat and Intel. And we have natural sciences represented. There's in the areas of genetics, in the areas of the microbiome, and modeling of disease. We have foundational data science problems in graph data analysis, explainable AI, large-scale multiple testing. And then we have problems represented in the social sciences as well, and even the humanities and arts. I have one on the fair policing, conflict and collaboration and online communities, spread of misinformation. And so each one of these may have up to, a dozen or so students supporting multiple teams. So what do the projects look like? So here's just a small sample of the projects. And of course, last year we had 25 projects. This year we have 76 projects. And you get a feel for, within these domains, what students are working on and building. And so in my last few seconds that I have, I want to actually advertise, which is in just under 2 weeks, the HDSI 2021 Senior Class Capstone Showcase, because they're actually wrapping up with their capstones, in the next week. And they'll be presenting them on a virtual conference, sort of a virtual poster session. And so we will be sending out more communication about that in the immediate future, right? And so I hope to see everybody there as well. Thanks.
Okay, thank you, Aaron. Let's move on to one of our recent graduates, Poonam Varkedi. Poonam was in the first graduating cohort, class of 2020. She's a data scientist with Viasat. So Poonam.
Hi, everyone. Can you all hear me?
Yes.
Cool. First off, I want to start by saying congratulations to everyone involved in building this institute to what it is today. I cannot believe that it's already been 3 years, and at the same time that it's only been 3 years. I remember attending the first annual celebration, and I was in complete awe of how much bigger it was than just like my major and the classes I was taking, and that there was research and faculty and industry connections and sponsorships. And that was crazy to me, and that just feels like yesterday. But at the same time, I'm like, thinking about how many of my peers that I know have gone on to like great jobs and great graduate programs, and how much this faculty has grown. And it's hard to believe that that's all been done in just a few like official years. I mean, I know the Institute was in the making before that, but how much it's exploded in the recent years is very impressive. One thing that I want to note, and I'm sure it's been brought up already, is that the first, second, and now the third graduating class are all going to be graduating in a pandemic. But that hasn't stopped a lot of them from getting great jobs, great graduate programs, like working on side projects to add to their portfolios. And I think a part of that is due to the Institute and how much it did prep us for the real world. I think where I want to talk to more is about how much the faculty and the staff have helped me and my peers get to where we are, even just like less than a year out of college. I'll start by saying that at my my second year of college, I attended an event that HDSI was having with Lyft. And first of all, that got me super excited about the career opportunities as a data scientist out there at companies like as big as Lyft. But that's one thing. I think what I want to say is that when I went to go check in, Maggie knew my name. Like she referred to me by my first name and I had never met her. And I was a little scared, a little taken aback. But it's only because she like was looking at my profile, what classes I'd taken, what I had left, like how to plan for the next few quarters. And she was already giving me advice. And I think that goes to show how much the faculty and the staff are putting it all there for the students. And there's so much support. But yeah, that's just one thing I wanted to say. Another major plus point of HDSI is that they really focus on cross-domain knowledge, as you all know, and how data science fits into that picture. So for my senior capstone project that Aaron just talked about, I had a PhD graduate student as my TA mentor person, and he was amazing in his domain, but he also knew data science and the skills and tools, and he was able to apply it to that domain. And I think getting that one-on-one guidance and mentorship from him was incredible. And I think it's one thing to like get a data set and clean it and do a model based on an assignment, but it's another thing to have that domain on there and try to figure out how to make the model that you build actually applicable to the domain and useful. And that's something I definitely learned in that class and am very much seeing in my job now at Biosat, trying to do cool data science stuff in a business setting is you can't really do anything unless you know the domain really well and you know like end to end what the business does, where are the weak points, where can you actually help? You can't just stick your nose in and start building things and hope it all works. So that's definitely, I mean, Aaron did touch on it just now, but a very important part of, I think, the HDSI program or undergraduate program. And I think even after graduating, I feel like I'm still part of the community. There's so many ways that I get to be involved with alumni, not only with keeping connected with other alumni, but also to faculty. The alumni committee has done such a good job with that, and everything has been remote. We've never had an opportunity to do anything in person, but even then, I get to talk to faculty every quarter for an event. I get to talk to students, whether that be networking, helping each other out get jobs, or re-prep, or working on project ideas. Just there's so much community, and I think that's a really cool point, a really cool part of this institute and major. And I think one final thing that I wanted to say is that I'm really excited for future industry partnerships with HDSI. Just last week, I was in a meeting talking about an internship opportunity for an HDSI student at a local nonprofit, and HDSI jumped on it. Like there was no hesitation, and they were ready to build that partnership and get real world opportunities for its students. And that's just Institute, and I'm really excited to see what else it has planned. But yep.
Okay, thank you, Poonam.
Thank you.
So hear from a former student doing so well, and now we're going to hear from a current student, Arunav Gupta, who is a sophomore, and he will talk to us about a project conducted via the HDSI undergraduate scholarship program. Arunav?
Thanks, Professor Politis. Let me just share my screen real quick. Okay, if everyone can confirm that they can see my screen. Okay, let's get started. Hi, everyone. So my name is Arnav. I'm currently a sophomore at UC San Diego. I'm a data science major. And I undertook this project last year as part of the HDSI undergraduate research scholarship with my advisor being Professor Isaac Martin from the Urban Studies Department. So just to jump right in with a quick motivating example, what you're looking at right now is a map of Cleveland, Cleveland, Ohio. And what you're seeing here is a dot representing every single person who responded to the 2010 US Census. And the dots are colored according to the race that they put down on the census. So for example, the dots that are colored blue correspond to those who listed themselves as white, green corresponds to African Americans, orange corresponds to Hispanic Americans, and so on and so forth. But what's really interesting about this map is you can see kind of the racial divides spatially amongst the different races. You can see, for example, there's kind of a vertical divide separating white and Black Americans within Cleveland. But even more interesting than that is sort of this. This is a map that was drawn in 1938, so 70 years ago. And it was drawn by the Homeowners Loan Corporation, which was a federally sort of sanctioned group that came out of the New Deal during the Great Depression. And what's really clear, so if I rewind and sort of put it back on there, you can see that the zones that they've marked on these maps very closely match up with the racial disparities that we see today. And so the goal of my research is to figure out why that sort of happened. But before we do that, let's first analyze what this map is. So like I said, this map was made by the Homeowners Loan Corporation in 1938, and it's what's known as a neighborhood risk map. So the zones that you see colored red correspond to people in those zones being considered too high of a risk to present mortgage loans to, and those in the green zones are the exact opposite. It's those that will most likely pay back those loans. And the goal of these maps was to sort of allocate mortgages during the Great Depression, obviously at a time when money was pretty scarce, and make sure that people would actually pay back their mortgages. The problem, however, was that these zones were often created with racial and socioeconomic factors included in them, which made them not very equitable and actually led to the forcing of minorities into certain zones within cities, which created things like ghettos and parallel lives. And it's responsible for a lot of the racial tensions that we're seeing, especially arise in recent years. So that brings me to the two key questions of this study. The first is, are Hoek redlining maps still relevant in describing racial segregation today? And second, if the answer to that first question is yes, can we quantify its relevance in various cities? So let's first talk about the methodology. The star of the show here is a process called Markov chain Monte Carlo, which is basically a way to take a specific type of state and then iterate probabilistically from that state to another state. And then if you do this enough times, you end up with a set of samples that you can use to essentially tell you more about the sample space that we're looking at. In this case, the sample space that we're looking at is the random generation of all kinds of districts, essentially all permutations of districts on a given map. So that's the first step of this process, is we take a map. In this case, you're looking at Oakland, California, and we essentially run a series of permutations essentially of the districts on these maps. So what you get effectively is you take a certain district or you take a certain map, and then you probabilistically generate a new map based on that first one. That's the Markov chain section of the process. Then from each of these maps, we move on to step 2. We generate a score from it. The score that we generate in this case is called a racial entropy score, where you can sort of think of it as a score of 0 corresponds to complete racial homogeneity between all of the districts, and 1 is the exact opposite. So we run this for hundreds of thousands of iterations. Actually, we ran it for 1 million iterations across 11 American cities. And then the next thing we do is we plot the univariate distribution of this. And we take the entropy score of the original Hoek map, the one that we initially started with, the redlining map, and we also plot it on the distribution. And this gives us 2 points of insight. The first point of insight is essentially how probable it is, sort of a p-value, so to speak, that the Hoek redlining maps produce the same levels of entropy as any randomly generated map would have on the same spatial space, on the same map or same spatial space. The second is we can look at the mean sort of difference between the mean of the distribution and that test value and see, generally speaking, how distant are the two, and we can use this to answer the second of those 2 questions. So now let's take a look at the results. So like I said, we ran this on 11 cities, and I think it's pretty clear. If you look at the distributions and you look at those red lines, you can see that in most cases, none of them happen to come from the same distribution. In all cases, all values are very, very statistically significant. The next thing you can also see from this is that the distances between the red lines and the means of the distributions is quite distant and quite small in different areas. So for example, if you look at San Diego, you can see that the distance between the red line and the distribution is very small. But if you look down here at Detroit, for example, you'll see that the distance is very large. And that also tells us a little bit about the predictive power of this Markov chain Monte Carlo. So let's move on to the key insights. Let's revisit those 2 questions and see how we can answer them now. So on the first one, are they still relevant in describing racial segregation today? The answer is a pretty resounding yes. In all 11 cities that were tested, 0 of the cities had a test score that appeared to have come from the Monte Carlo distribution, which let us know that out of the millions of random maps that we could have possibly generated, no map better predicted racial segregation in 2010 better than those 1938 maps drawn 70 years ago. And then moving on, second, can we quantify its relevance in the various cities? And the answer to that is somewhat yes, more relatively. In this case, the Hulk maps were able to predict the segregation in Detroit 6.44 times more accurately than they were to in San Diego. And this is directly on account of the difference between that distribution and the test score that we found. So why is this useful? I think when most people look at those maps, they already know that they appear sort of discriminatory, but why is it useful to assign a methodology to it? Well, the first one is it provides a really cool statistical sort of proof of concept that this is probably an indication that the federal government is somewhat responsible for the negative racial outcomes of racial minorities in America. That's the first point. The second point is that it's a very modular statistic. So we can not just look at racial disparity, we can look at income outcomes. We can look at education outcomes, for example. We can even swap out the statistic of choice. Instead of using entropy, we can use indexes of dissimilarity or any other statistic that you could prefer, which makes this a very powerful benchmark that cities and governments can use when they implement policy. For example, when Fair Housing Acts are passed, we can run the statistic beforehand, and we can also run the benchmark after the passing of the policy to determine if that policy actually ended up making housing more equitable and equal. And I think this is a really cool application of how Markov chain Monte Carlo, and more specifically data science, can be used in sort of intersectionality with policy, and in order to make essentially our neighborhoods more equitable and more inclusive places. And so for that, there's a lot I essentially could not get through in this very short summary of this study. But if you do have any questions, please do email me at aronofg@ucsd.edu, and I'll be more than happy to engage with you on the study itself. I'm actually writing a paper as a draft right now, so if you're interested, I can also send that to you. But for now, thank you so much for listening.
Well, what great stuff. Thank you, Arnav. Now moving on to Margaret, also known as Maggie Zulke. So Poonam actually referred to Maggie being on top of it and helping her with her studies and so forth. And yeah, Maggie was actually one of the pillars of the undergraduate program for a while. Now she's moved to career services. Maggie, yeah.
Thanks so much. So as Dimitri said, I'm Margaret Zulke, also known as Maggie, and I'm currently the career advisor and alumni relations specialist for the Collegiate Data Science Institute. I'm so excited to share a little bit about this new branch of support offered through HDSI before diving into the placement data of our first graduating cohort, the class of 2020. So HDSI Career Services is designed to support employers, students, and alumni. The main goals of this support is to connect talent to opportunities through diverse pathways that alleviate industry pain points, to help students navigate their career options and develop confidence in their career competencies as young professionals, and to build and utilize our emerging alumni community as potential pipelines in the future. With the launch of the HDSI Career Services shortly after graduating our first cohort of students in spring 2020, we have an exciting opportunity to immediately track our talent placement. We use this information to guide current students on their career options, as well as to help guide an understanding of where our talent can be utilized to make an impact within the field. Overall, we've seen our alumni pursue a graduate program, participate in research, or pursue placement in the workforce immediately after graduation. You can see here that 77% of our first cohort chose to pursue placement in industry, 2% entered research, and 21% were placed in graduate school. For this particular cohort, it's important to remember that the undergraduate program launched their sophomore year. So essentially all students completed the curriculum in 3 years in order to graduate on time. I saw this as one of the main contributing factors when this cohort was deciding the next step after graduation. For many, they saw graduate school as an opportunity to further develop their skill set and domain knowledge. For others, they wanted more experience before determining how to focus their education and training at the graduate level. And also, we saw students excited to start applying their skill set outside of the classroom with no plans to continue their education in the future. Focusing first on our graduate school placement, here you can see the graduate programs which accepted students from our first cohort. One thing I'd like to point out is that 100% of these graduates entered a master's level program rather than pursuing a PhD. And I point that out because I know the statistic will soon change based on conversations with younger students within the program. Taking a closer look at our industry placement data, the gray bar is the percentage compared to the alumni who chose to enter industry after graduation, and the orange bar is the percentage compared to the number of alumni in total. As you can see, over half of the alumni who chose to enter industry after graduation have full-time employment at this time, with a small percent pursuing internships that are designed to lead to full-time employment in the future. A question I'm frequently asked by both students and employers is, what specific roles are we seeing alumni selected for? In other words, how prepared are the individuals who immediately enter the workforce after completing their undergraduate training? With the specific titles, or while the specific titles may vary, we've noticed a trend for the roles to include the terms analyst, engineer, or developer within the title. Additionally, we see 11% of our alumni working full-time secure positions with the specific title of data scientist. If we further examine the titles, including the term engineer, that make up almost half of our data, we see that half of these alumni are securing positions that include software engineer within the title. For reference, a few of the other engineering-related titles included machine learning engineer and growth engineer. Here you'll see some of the companies where our alumni have found full-time employment, and I'd like to give a special shout out to our industry partners, Viasat, Sandag, Deloitte, Epicor, and Thermo Fisher, who are included on this list. And I'm happy to share the full-time placements we're already seeing for our next cohort, the class of 2021. Again, special thanks to our industry partners, Deloitte, Intel, and Thermo Fisher, who are included on this list. If you're interested in learning more about our talented populations of students and alumni, we have helpful resources on our new HDSI Career Services page of our website. Here you'll find demographic information, a skill development by year level resource created with faculty to identify the expected skill set of a student who has followed the recommended curriculum plan by year level, and information on how to connect with our students and alumni, including an opportunity submission form and more information on our senior capstone project. I'd like to thank you all for listening in to learn more about HDSI Career Services and our HDSI talent. And here's my contact information in case there are any follow-up questions.
Thank you, Maggie. And we are on time, so I will give the floor to Rajesh for the closing.
Thank you, Dimitris. So I was listening to Arnav's talk about Monte Carlo Markov chain models. And I was thinking, this kid has 2 more years to go with us. That's the kind of preparation we give to our students. Within first 3 years, they're done with majority of the courses. And during the process, they are majority of the required courses. During the process, they're hands-on. They're asking questions. They might not know how to get the answer, but then they would know when an answer makes sense. So there are 3 organizing principles behind this HDSI plan. One is it took a very unified view of data science. We did not call data science as data science for X or Y. Data science at all levels in all areas. And that reflects itself. If you think about it, the 25 faculty appointed to HDSI with teaching responsibilities are supported also by another 23 faculty who have what is technically known as 0% appointment, but it's really a full faculty appointment. So 48 faculty drawn from 18 different departments, or within partial appointments with 18 different departments. There hasn't been another academic unit like this in any historical context that I know. And we are not just a research institute. Interdisciplinary research is actually one of the easy things to do. is putting people together who share some interest on problems or whatever. It's the transdisciplinary teaching that is the biggest challenge. And Aaron Frankel, our teaching assistant professor, laid it out to us. And it's not just for a small group of people. It is currently the 8th largest major on campus. We teach about 5,000 students in our classes, similar to what Jennifer Shays mentioned, the division of computing data science does at Berkeley. So we take a holistic view of the discipline. The second organizing principle is it is student-centered. We called it an institute for a variety of reasons to make sure that it remains the hub for the entire campus. But the importance of students' courses, programs was not lost on us. That was the job number one. So we created the data science undergraduate program. We created the data science graduate programs, now online masters and PhD program. And as I speak to you, we are close to finalizing details of a pretty exciting bachelor's and master's program combined, where the data science students spend another extra year and they get a degree in business analytics from Reddy School of Management. By choosing the right electives in their 4th year and spending another extra year. So 4+1 programs that was called combined BSMS program. That will not be the only one in the coming years. Definitely an MS and MD program will be like that. That's also under planning currently. So very student-centered. All the talent that we collect, all the talent we engage, all the talent we attract is to meet that need first. The third organizing principle has been highly experiential and experimental. From the day a student walks in, the first instructor very likely they're going to see is Brad Wojtek or Marina Langlois or Jenny Tiefenbrook or Aaron Frankel. Each one of them impresses upon the need to understand, to ask the right questions. They may not know how to solve it, but they start to understand what the right questions that can be answered algorithmically through data. So highly experimental. Our vision is, my vision is that by the time a student graduates with a capstone, capstones are extremely expensive in planning, as you probably saw the details. They have not only a list of grades on a piece of paper, but a portfolio of projects on a GitHub or something that they can walk the potential employers through or their own future plans as to what they're capable of. So this does not happen without an excellent team around me. And as the Chancellor said, it is the quality of the people who have managed this. I want to just take a few moments just to thank them, not only for putting the program together, but really the Institute together. In many ways, HDSI, in fact, not many ways, literally it is. HDSI is like a startup inside a university. In other words, the individuals we have are not specialized by functions, but they really take on any and every task. It does everything that a department does. It does most things that a school does. And then it also does, we're beginning to do the projects that any center does. So when you take all 3 different organizations, put them together as a startup, which means that the limited staff we have change their hat and change their roles very often. And they are the key to what has happened in building this institute together. The 2 of them you saw in front are associate directors Dimitris Politis and Jenny Disa. It is fair to say that no 48 hours go by, if not 24. 48 I have to say, because I think I need to give them some rest over the weekend, when I haven't talked to at least one of them, if not both. So they have been on top of all of those activities. The 6 faculty that you saw present is only 1/3 of the faculty that we have recruited, and only 1/8 of the faculty who are actually active in HDSI. And while they were presenting, I was thinking, no two of them will be in the same department if HDSI did not exist. So this got to make an impact on what the discipline will be in years from now, in decades from now. So I want to just thank a number of our wonderful staff who actually have been making this, who have made this event possible. Even as we were going through, they are working on frantically on the back end to making sure everyone is able to enter. If there is a Zoom bombing attack or something like that, we are ready. I couldn't do anything without Logan Wiedenhofer, who's technically an executive assistant, practically wears all the hats. And he works with another very close collaborator, Eric Snee. And Eric and Logan together have been heroes of putting this event together. I wish we had one of those Hollywood style crowd clapping or something so that we could fill the silence, but you can imagine clapping by the rest of the HDSI community to them. Bobby Gordon handles our communications and is always often the person to get most nervous about if the video doesn't have the right audio and so on, but has been working very hard in pulling this together. With our MSO. MSO is an internal technical term within UC, but basically it means manager of all things, Jen Morgan, who runs the entire operation. We have a number of our staff, you saw some of them, whose dedication, Maggie and Megan was not here, their dedication has made what is student advising possible. It is not an accident when Poonam mentioned that the advisor knew her name. We require every single student be individually advised in person by our staff. And that will not change even with our graduate program. With our graduate program, not only they will have a staff advisor, but they will also have faculty advisor in addition to their own research advisor. It is extraordinarily important. It is very important if we are to maintain the quality of higher education as we have done, that we manage to we spend the necessary time and effort in get to know our students individually, advise them individually as you would to our own children if they would listen, and create programs that creates the talent for what the society will become tomorrow. So that's all I had to say. Thank you so much for your attention. We will record, we are recording this event, and at some point it will be made available internally or externally. In the meantime, definitely the next celebration, I hope, will be in person, and we'll make sure that there is chocolate for everyone, for that makes a difference from what we learned today, at least on causal inference. Thank you. All right, Dimitris.
Thank you all. Thank you. It was wonderful.
Thank you. We'll stop you. Thank you.